Something from beyond our solar system is crossing Earth's orbit right now. It's traveling at 137,000 miles per hour, and by the time you finish watching this video, it will already be past us, racing back into the dark between the stars. Its name is 3I Atlas, and it is only the third object in recorded history confirmed to have visited our solar system from interstellar space. Not a meteor, not a stray asteroid kicked loose from the Kuiper belt. An actual traveler from another star system, passing through our cosmic neighborhood on a trajectory so fast and so steep that the sun's gravity cannot hold it. It will loop around once, swing past Earth at a distance of 170 million miles, and then vanish forever into the galactic void. NASA spotted it on July 1st, 2025. Within hours, they knew something was wrong with the numbers. The velocity was too high. The orbit was hyperbolic, not elliptical. This thing wasn't circling, it was escaping. And when Hubble turned to image it in August, the data it sent back raised more questions than answers, because 3I Atlas is behaving in ways interstellar objects are not supposed to behave. It has no tail, no visible coma. Its shape appears elongated, maybe tumbling, and its spectroscopic signature doesn't match what astronomers expected from a comet born around an alien sun. Planetary defense systems have been tracking it around the clock. Observatories across 6 continents are coordinating data in real time, and every scientist involved knows the same uncomfortable truth. This object will be gone in days, and we may never get another chance like this in our lifetimes. So what exactly is 3I Atlas? Where did it come from? And what has it already taught us about the universe we thought we understood? This is that story. Welcome to Magnetic Space. If you're new here, please subscribe. We make these documentaries every day, and honestly, we'd love to have you along for the ride. Before we begin, tell us in the comments where you're watching from and what time it is there. Now settle in. This is going to be a good one. On the 1st of July 2025, a machine noticed something wrong. The machine was a telescope, one of 4 identical instruments scattered across 2 hemispheres, part of a system called ATLAS, which stands for Asteroid Terrestrial Impact Last Alert System, built to watch the sky for anything that might one day end civilization as we know it. The telescope that caught this particular signal sits in Rio Hurtado, Chile, a valley carved into the Andes, about 400 kilometers north of Santiago. Dry air, high elevation, dark skies, the kind of place where you build instruments designed to see things before anyone else does. What it saw that night was moving. Not drifting, not floating along in the lazy gravitational waltz that governs 99.9% of everything in the solar system. Moving, fast, faster than anything has a right to move unless it came from somewhere else entirely. The object was logged into the system as 3I Atlas. The 3I part is what matters. It stands for Third Interstellar, as in the third confirmed visitor from outside our solar system since humanity started keeping track. Third object ever detected that was born around a different star, spent millions or billions of years drifting through the freezing void between solar systems, and then wandered into our neighborhood by accident. The Atlas telescope flagged it immediately because its trajectory made no sense. Trajectories in the solar system follow rules. Objects move in ellipses, in parabolas, in long looping orbits that eventually bring them back around, closed paths, predictable geometry. Even comets from the distant Oort cloud, objects that take tens of thousands of years to complete a single orbit, still follow curves that close. They leave, but they return. This one wasn't coming back. The path was hyperbolic. That word has a specific meaning in orbital mechanics, and it is not a metaphor. A hyperbolic trajectory is an open curve. It describes an object moving so fast that the sun's gravity cannot hold it. The object comes in, swings past, and leaves forever. No second lap, no return trip. One pass through the solar system, and then an eternity of empty space in the opposite direction. When the Atlas software calculated the orbit and saw that hyperbolic shape, it did what it was trained to do. It sent alerts. Within hours, observatories on 3 continents were swiveling their instruments toward the same patch of sky, trying to confirm what the Chilean telescope had found. They confirmed it. At the moment of discovery, 3I Atlas was traveling at roughly 137,000 miles per hour. Some sources round that to 61 kilometers per second. Either way, the number is absurd. For context, the Earth orbits the Sun at about 67,000 miles per hour. The fastest human-made object ever built, the Parker Solar Probe, hit a top speed of about 430,000 miles per hour, but only by falling toward the Sun and using its gravity like a slingshot. Natural objects, the rocks and ice balls that were born in our solar system and have been circling the Sun for 4.5 billion years, do not move at 137,000 miles per hour unless something has gone catastrophically wrong. This object was not catastrophically wrong. It was simply not from here. The speed is the giveaway. There is a threshold. If you measure an object's velocity relative to the Sun, subtract out all the contributions from planets and moons and orbital mechanics, and you are still left with a significant excess, you are looking at something that did not start its journey in this solar system. Something gave it a push a very long time ago in a place we cannot see, and it has been coasting ever since. NASA's Jet Propulsion Laboratory, which tracks every known object in the solar system and calculates their future paths, ran the numbers. The result was unambiguous. The object's velocity could not be explained by any interaction with the Sun or planets. It was already moving too fast when it arrived. The hyperbolic orbit, the excess speed, the trajectory that pointed backward into interstellar space. Every measurement said the same thing. This object came from outside. That makes it rare, extraordinarily rare. For most of human history, we had no idea interstellar objects even existed. The concept was not controversial. Astronomers assumed that space between the stars must be full of rogue planets, dead comets, chunks of rock and ice that had been ejected from their home systems during planetary formation and sent wandering. The math said those objects should be out there. We just had no way to see them. Space is large. Interstellar objects are small and dark, and unless one happens to pass close enough to the Sun to light up or close enough to Earth to be detected by a survey telescope, it remains invisible. The first confirmed interstellar visitor arrived in October 2017. Astronomers at the University of Hawaii spotted it using the Pan-STARRS telescope and named it 1I Oumuamua, a Hawaiian word meaning scout or messenger. The name fit. Oumuamua was moving at about 58,000 miles per hour relative to the Sun, again far too fast to be bound by solar gravity. Its trajectory was hyperbolic. It came from the direction of the constellation Lyra, passed within about 15 million miles of Earth, and then shot back out toward the constellation Pegasus. The discovery triggered an immediate global observing campaign. Telescopes all over the planet, including the European Southern Observatory's Very Large Telescope in Chile and NASA's Hubble Space Telescope, tracked Oumuamua as it raced away from the Sun. Researchers had only a few weeks to study it before it faded into the background noise of distant stars. What they found was strange. Oumuamua was elongated, possibly 10 times longer than it was wide. That shape was unusual but not impossible. Stranger was the fact that it seemed to be accelerating slightly as it moved away from the Sun. Not a lot, just a tiny push, barely detectable, but enough to throw off the orbital predictions. Marco Micheli, a researcher at the European Space Agency, later said that high-precision measurements revealed there was something affecting the object's motion other than the gravitational forces of the Sun and planets. Davide Farnocchia at NASA's Jet Propulsion Laboratory concluded that the extra acceleration was consistent with outgassing, jets of gas escaping from the surface the way a comet behaves when it heats up near the Sun. That explanation made sense, but it also raised new questions. Oumuamua did not have a visible coma, the cloud of gas and dust that typically surrounds an active comet. It looked more like an asteroid. If it was outgassing, the jets were either too faint to see or pointed in a direction that did not produce a visible tail. Some scientists accepted the comet explanation, others were not convinced. A few suggested more exotic possibilities, ideas involving light sails or artificial objects, proposals that made headlines but found little support in the data. Oumuamua left the solar system before anyone could settle the debate. By mid-2018, it was too faint to observe. The mystery remains open. 2 years later, in August 2019, amateur astronomer Gennady Borisov spotted a second interstellar visitor using a telescope he had built himself in Crimea. The object was designated 2I Borisov, and unlike Oumuamua, this one behaved exactly like a comet. It had a visible coma, a tail, spectroscopic signatures of water and carbon monoxide outgassing, the whole package. Borisov was easier to study because it was discovered earlier in its approach, giving astronomers months to observe it before and after it swung past the Sun. By the time it left, scientists had gathered enough data to confirm that it was chemically similar to comets born in our own solar system, just older and from somewhere else. Borisov proved that interstellar comets are real, that they behave the way theory predicted, and that with enough time and the right instruments we can study them in detail. It also proved that these visitors are not one-offs. If we found 2 in the span of 2 years, there are probably thousands passing through the solar system at any given time, most of them too small or too far away to detect. Now we have a third. 3I Atlas is moving faster than either of its predecessors, 137,000 miles per hour. That is more than twice the speed of Oumuamua. The difference matters because speed tells you something about where an object came from and how long it has been traveling. The faster an object moves relative to the local standard of rest, the more likely it is to have come from a distant part of the galaxy or to have been accelerated by a close encounter with a massive star early in its history. Speed is a fossil record written in motion. The discovery of 3I Atlas was unusual in another way. Most interstellar objects are not recognized immediately. Oumuamua was discovered after it had already passed perihelion, the point in its orbit closest to the Sun. By the time astronomers realized what they were looking at, it was already on its way out. Borisov was spotted earlier, but even then it took several days of follow-up observations to confirm that its orbit was hyperbolic. The process of identifying an interstellar object typically involves detecting something odd, calculating a preliminary orbit, gathering more data, recalculating, and slowly building confidence that the orbit is not going to close. 3I Atlas skipped most of that process. Its trajectory was immediately hyperbolic. The speed, the angle, the shape of the orbit, all of it screamed interstellar from the moment the first data came in. That almost never happens. It suggests the object was either moving unusually fast or approaching from an unusually steep angle, or both, making the geometry impossible to misinterpret. Survey telescopes like Atlas are designed to catch exactly this kind of event. They scan the sky repeatedly, imaging the same patches of stars night after night, looking for anything that moves or changes. Asteroids, comets, supernovae, variable stars, anything that was not there last week. When something new appears, the software flags it and calculates a rough orbit. If the orbit looks dangerous, meaning the object might pass close to Earth, the alert goes out immediately to the planetary defense community. If the orbit looks weird, meaning hyperbolic or otherwise non-standard, it goes out to the broader astronomical community. 3I Atlas triggered both alerts. The object is not a threat. NASA has been clear about that from the start. The closest it will come to Earth is somewhere between 1.6 and 1.8 astronomical units. 1 astronomical unit is the distance from the Earth to the Sun, about 93 million miles. So at its nearest, 3I Atlas will pass roughly 150 to 170 million miles away. Far enough that it poses no danger, far enough that even seeing it requires serious optical equipment, but close enough and bright enough that professional observatories can track it for weeks or months and gather detailed measurements. That window is what makes this discovery valuable. Unlike Oumuamua, which was spotted on its way out and faded quickly, 3I Atlas was caught early enough that researchers will have time to study it properly. Spectrographs can measure its chemical composition. Photometry can track its brightness and look for variations that might reveal its rotation or surface features. Astrometry can refine the orbit and determine exactly where it came from, because that is the next question. Where did this thing start? Interstellar space is not empty. It is full of stars, hundreds of billions of them in our galaxy alone. Somewhere out there, maybe a few hundred light years away, maybe a few thousand, there is a star that this object used to orbit, a system where 3I Atlas formed, either in a disk of gas and dust around a young star, or in the outer reaches of a planetary system that later became unstable. Something, a gravitational interaction with a giant planet, a passing star, a binary companion, kicked it out, gave it a push strong enough to escape the star's gravity and sent it drifting into the void. From there it coasted for millions of years, possibly tens of millions, moving at interstellar speeds through a galaxy rotating at hundreds of kilometers per second. The object we are seeing now is a time capsule, a frozen artifact from another system, another era, carrying information about the conditions and chemistry of a place we will likely never visit. That is what makes interstellar objects scientifically precious. They are the only samples of other solar systems we can study up close without building a starship. Every measurement we make of 3I Atlas is a measurement of something that was not made here. Its ice, if it has ice, was frozen in a different protoplanetary disk. Its rock, if it has rock, was formed under a different star. The ratios of elements, the isotopes of hydrogen and oxygen and carbon, the organic molecules that might be locked in its structure, all of it is data from somewhere else, and we have days, maybe weeks, to get it. The scramble started the moment Atlas sent the alert. Observatories around the world began reprioritizing their schedules, pointing instruments toward the coordinates, requesting time on larger telescopes with better instruments. The European Space Agency put out a notice. NASA's Jet Propulsion Laboratory updated its tracking database. Amateur astronomer networks were notified. The planetary defense community ran simulations to confirm there was no impact risk. And researchers who spent their careers studying small bodies in the solar system suddenly had a new target list with exactly one object on it. Because no matter how many times we detect one of these visitors, each one feels like the first. Each one carries the same electric jolt of realization. Something from out there is passing through here, right now, while you are reading this. A rock or a comet or a fragment of a planet that formed in a system we cannot name, around a star we cannot see, is crossing the solar system at 137,000 miles per hour, and for a brief moment, just a blink in cosmic terms, it is close enough that we can point our best instruments at it and ask it questions. What are you made of? Where did you come from? How long have you been traveling? Sometimes the object answers. Sometimes it just keeps moving. Either way, the clock is already ticking. The moment at last sent the alert, the clock started ticking. Not a metaphorical clock, a real one, measured in days and weeks and the slow rotational grind of telescope schedules that were suddenly obsolete. Within 12 hours of the discovery, 7 major observatories across 4 continents had confirmed the object's existence and trajectory. Within 48 hours, a dozen more had joined. By the end of the first week, the global astronomical community had effectively dropped everything else and pointed every available instrument at a patch of sky roughly the size of a full moon, tracking a dot of light that was already fading as it moved. This is not how astronomy usually works. Telescope time is precious. Observatories like the European Southern Observatory's Very Large Telescope in Chile or the Keck Observatory in Hawaii operate on schedules booked months or years in advance. Every night is allocated to a specific research team studying a specific target. Galaxies, exoplanets, supernovae, black holes. Proposals are submitted, reviewed, ranked, and assigned time based on scientific priority. The system is slow, careful, deliberate. It has to be. There are far more scientists with good ideas than there are nights of clear sky to go around. Interstellar objects break that system. When something shows up moving at 137,000 miles per hour on a trajectory that will carry it out of the solar system forever, scheduling committees get overruled. Directors' discretionary time gets invoked. Observations get bumped. Teams that had waited years for their chance to study a distant quasar or a variable star suddenly get an email informing them that their time has been reassigned to a higher priority target, an object that did not exist in any catalogue 48 hours ago. Some of those researchers are understanding, some are not. Either way, the telescopes turn. The first challenge is simply seeing the thing. Interstellar objects are small, dark, and moving fast. 3I Atlas is somewhere between 440 meters and 5.5 kilometers across. That range exists because measuring the size of an object this far away is maddeningly difficult. You cannot resolve its shape. Even Hubble, which confirmed the object's cometary activity in late August, could not image the nucleus directly. What you see is a point of light, a few pixels on a detector, maybe a faint smudge if the object is outgassing and producing a coma. From that tiny signal, you have to infer size, shape, composition, rotation, and activity level. The standard method involves measuring the object's brightness and making assumptions about how reflective its surface is. Darker surfaces reflect less light, which means the object has to be larger to produce the same brightness. Brighter surfaces mean smaller objects. The range of possible sizes for 3I Atlas spans more than an order of magnitude, because we do not know whether we are looking at a dark carbonaceous chunk or a brighter icy body. Both are plausible, both fit the data. We will not know for sure until we gather more spectroscopic information, and that requires instruments that can split the faint light from the object into its component wavelengths without losing the signal entirely. The second challenge is speed. 3I Atlas is not sitting still while we point telescopes at it. It is moving relative to the background stars at a rate fast enough that long exposure images, the kind you need to collect enough light from a dim object, start to blur. The object becomes a streak instead of a point. Tracking systems have to compensate by moving the telescope at exactly the same rate the object is moving across the sky. That sounds simple. It is not. The tracking software needs accurate orbital data, and orbital data for a newly discovered object is always uncertain at first. Every observation refines the orbit, which changes the predicted position, which means the next telescope has to update its pointing coordinates in real time. This is one reason why survey telescopes like Pan-STARRS and Atlas are so critical to early detection. Pan-STARRS stands for Panoramic Survey Telescope and Rapid Response System. It consists of 2 telescopes, one in Hawaii and one being commissioned elsewhere, each equipped with a camera containing nearly 1.5 billion pixels. The instruments are designed to image large sections of sky repeatedly, scanning the same areas every few nights to catch anything that has changed. Asteroids, comets, supernovae, variable stars, transient events of any kind. The software compares new images to old ones and flags anything that was not there before. When Pan-STARRS or Atlas spots something moving, the detection gets logged into a database and cross-checked against known objects. If no match is found, the object gets a provisional designation and the data gets distributed to a network of observers who can follow up. That network includes professional observatories, university telescopes, and amateur astronomers with serious equipment. The goal is to get as many independent observations as possible in the shortest amount of time, locking down the object's position and trajectory before it moves out of range. For 3I Atlas, that process happened faster than usual. The object's hyperbolic orbit was so obvious from the first few observations that confirmation came within days instead of weeks. By the time NASA's Jet Propulsion Laboratory issued its official statement on the trajectory, observatories around the world were already queuing up follow-up observations. Spectrographs, photometers, astrometric instruments, every tool available pointed at the same target. Spectroscopy is where the real science happens. A spectrograph takes the light from an object and spreads it out into a spectrum, the same way a prism spreads sunlight into a rainbow. But instead of colors, what you see is a pattern of bright and dark lines. Each line corresponds to a specific element or molecule, either emitting or absorbing light at a characteristic wavelength. Hydrogen has its lines, oxygen has its lines, water vapor, carbon monoxide, methane, dust, all of them leave fingerprints in the spectrum. For 3I Atlas, the spectra revealed the signature of a comet. Water vapor was detected escaping from the nucleus, along with traces of dust and other volatiles. That confirmed the object was not just a bare rock, but an active body with ice sublimating as it warmed up on approach to the sun. Sublimation is the process where a solid turns directly into a gas without passing through a liquid phase. On Earth, dry ice does this. Carbon dioxide frozen at -78 degrees Celsius will turn directly into vapor if you leave it out at room temperature. On a comet, water ice behaves the same way. As the object gets closer to the sun and the surface temperature rises, ice buried just beneath a thin layer of dust begins to vaporize. The gas escapes through cracks or pores in the surface, carrying dust grains with it. That gas and dust forms a glowing cloud around the nucleus called a coma, and if enough material escapes, it can be pushed away from the sun by solar radiation and the solar wind to form a tail. Hubble detected the coma. Spectroscopy confirmed the composition. Together, those observations told scientists that 3I Atlas is behaving like a typical comet, just one that did not originate here. Photometry measures brightness over time. By tracking how the light from an object changes, astronomers can infer its rotation rate, its shape, and whether it has active regions on its surface that brighten or dim as they rotate into and out of view. For 3I Atlas, photometric data has been limited so far because the object is faint and the signal is noisy. Small changes in brightness get lost in the background unless you have a very large telescope with excellent detectors and a lot of observing time. Still, preliminary light curves, the graphs that plot brightness against time, show some variation. That variation could be due to rotation, could be due to outgassing from specific jets on the surface, or could just be noise. More data is needed, and the window to get that data is closing. Astrometry is the measurement of position. It sounds mundane. It is not. Knowing exactly where an object is at a given time and how that position changes is how you calculate its orbit. Astrometric measurements for 3I Atlas have to be extraordinarily precise because even a tiny error in position translates into a large error in the predicted trajectory weeks or months later. Professional observatories use automated systems that compare the position of the target object against a catalogue of background stars whose positions are known to fractions of an arcsecond. 1 arcsecond is 1/3600th of a degree. Typical astrometric accuracy for a bright object is around 1/10th of an arcsecond. For a faint, fast-moving object like 3I Atlas, getting that precision requires multiple observations from multiple sites, averaged together to reduce random errors. That is where amateur astronomers come in, not all of them. The object is too faint for small backyard telescopes. But there is a tier of serious amateur observers equipped with telescopes in the 10 to 16-inch range, mounted on computerized tracking systems, equipped with CCD cameras and sometimes even spectrographs. These instruments are not toys. They are capable of doing real science, and there are hundreds of them scattered around the world, covering longitudes and latitudes that professional observatories do not. When a bright comet or asteroid appears, amateur astronomers provide crucial supplemental data. They fill gaps between professional observations. They provide confirmation when a discovery is uncertain. They catch outbursts or sudden changes in activity that might happen between scheduled professional observing runs. For 3I Atlas, several amateur networks, including groups coordinated through platforms like the Minor Planet Center and the Comet Observation Database, contributed early astrometric and photometric measurements that helped refine the orbit in the critical first week after discovery. Citizen science efforts have expanded in recent years with projects like Zooniverse, which allows non-specialists to help classify astronomical data. While 3I Atlas is too faint and technical for most citizen science platforms to contribute directly, the infrastructure built by those platforms, automated detection algorithms, data sharing networks, and real-time collaboration tools has made the entire field more responsive. When something like this shows up, information spreads faster, observatories coordinate better, data gets analyzed more quickly. The urgency comes from something called the observational window. For any given object, there is a limited period during which it is visible and bright enough to study. That window is determined by several factors: distance from Earth, distance from the Sun, position relative to the Sun as seen from Earth, and brightness. For 3I Atlas, the window opened in late August 2025 when the object was discovered. At that point, it was inbound, moving toward perihelion, the closest point in its orbit to the Sun. That perihelion was predicted for late October 2025 at a distance of about 1.4 astronomical units, roughly 210 million kilometers. That is inside the orbit of Mars, but well outside the orbit of Earth. As the comet approached perihelion, two things happened. First, it got brighter because it was closer to the Sun, and more sunlight was reflecting off its surface and coma. Second, it became harder to observe because it was moving into the same part of the sky as the Sun. By late September, the object was too close to the Sun's glare for ground-based telescopes to see it safely. Pointing a telescope near the Sun is dangerous. The concentrated sunlight can damage detectors, fry optics, and in the case of optical telescopes without proper filters, blind anyone looking through an eyepiece. That meant the first observational window closed in September. The object disappeared into the solar glare and would not reappear until December, after perihelion, as it moved back out into darker sky on the far side of the Sun. By that time, it would be receding from both the Sun and the Earth, dimming steadily as it moved away. The second window, from December 2025 through mid-2026, would be the last chance to gather detailed data. After that, the object would be too faint for all but the largest telescopes, and eventually it would fade below detectability entirely, leaving the solar system forever. So the race was on. Everything that could be learned about 3I Atlas had to be learned in two narrow windows separated by months, with the best opportunity already behind us by the time most of the scientific community realized what they were looking at. This is not unique to 3I Atlas. It is the story of every interstellar object ever detected. Oumuamua was discovered after perihelion when it was already leaving. Observers had weeks, not months, to study it before it faded. Borisov was luckier. It was discovered earlier and stayed bright longer, giving astronomers time to coordinate a detailed observing campaign. But even Borisov eventually faded, and by early 2020 it was gone. The Vera, the 100th. Rubin Observatory, currently under construction in Chile and expected to begin operations soon, is designed specifically to catch more of these objects earlier. Rubin will survey the entire visible sky every few nights using a camera with 3.2 billion pixels, the largest digital camera ever built for astronomy. Its wide field of view and sensitivity will allow it to detect fainter, faster-moving objects than any previous survey telescope. Simulations predict that once Rubin is operational, it will find dozens of interstellar objects per year, maybe more. Instead of scrambling to study 3 objects over the course of a decade, astronomers will have a steady stream of targets, but Rubin is not online yet. For now, the community is working with what it has: Atlas, Pan-STARRS, professional observatories with flexible scheduling, and a global network of observers who drop everything when something like this appears. The coordination required to make that work is invisible to most people. There are email lists, Slack channels, shared databases, automated alert systems. The Minor Planet Center, operated by the International Astronomical Union, serves as a central clearinghouse for observations of small solar system bodies. When a new object is detected, observations are submitted to the Minor Planet Center, which calculates preliminary orbits and distributes updated predictions. Other groups, like NASA's Center for Near-Earth Object Studies, focus specifically on objects that might pose an impact risk. For 3I Atlas, the risk was 0, but the trajectory was strange enough that the object got flagged immediately and added to high-priority tracking lists. Behind the scenes, researchers are writing observing proposals in real time, submitting requests for directors' discretionary time, calling in favors with colleagues who have access to better instruments. Some observations happen because someone sent an email at 2 in the morning to a telescope operator on another continent asking if they could squeeze in an hour of imaging before sunrise. Others happen because a graduate student staying late in a university observatory happened to be testing new software and decided to point the telescope at the new object, just to see what would happen. Science at this level is messier and more human than most people realize. It is not a smooth, coordinated machine. It is a chaotic, collaborative scramble where timing and luck matter as much as skill and resources. By mid-September, before the object disappeared into the sun's glare, the astronomical community had accumulated enough data to confirm several key facts. The orbit was hyperbolic with an eccentricity greater than 1, meaning the trajectory was open and the object would not return. The velocity at discovery was roughly 61 kilometers per second relative to the Sun, well above solar escape velocity. The object showed clear signs of cometary activity with a detectable coma and spectroscopic evidence of water vapor and dust. Its size was estimated to be somewhere between 440 meters and 5.5 kilometers in diameter, with the uncertainty driven by unknown surface properties. And its origin, traced backward along its trajectory, pointed toward the galactic center, a different direction than either of the previous interstellar visitors. That last detail is worth pausing on. Oumuamua came from the direction of the constellation Lyra. Borisov came from the direction of Cassiopeia. 3I Atlas is coming from the direction of Sagittarius, roughly toward the center of the Milky Way. That does not mean it came from the galactic center itself, which is tens of thousands of light-years away. It means its trajectory, when traced backward and corrected for the motion of the Sun through the galaxy, points in that general direction. The object could have been ejected from a star system anywhere along that line of sight, anywhere from a few hundred to a few thousand light-years away. Without more information, we cannot pinpoint its origin more precisely than that. The diversity of arrival directions tells us something important. Interstellar objects are not streaming in from a single source. They are coming from all over the galaxy. That matches theoretical predictions. Planetary systems are messy during formation. Gravitational interactions between planets, especially giant planets, can fling smaller bodies out of the system entirely. Over billions of years, the galaxy fills up with these ejected objects, forming a kind of background population of rogue comets, asteroids, and possibly even rogue planets drifting through interstellar space with no star to orbit. Every so often, purely by chance, one of them passes close enough to another star to be captured temporarily or, more commonly, to swing past and keep going. That is what we are seeing with 3I Atlas. Not an intentional visitor, not a messenger, just a random piece of interstellar debris that happened to pass through the solar system at a time when we had the instruments to detect it. But random does not mean unimportant. Every interstellar object is a sample of material from another system. The ice on 3I Atlas froze in a protoplanetary disk that formed around a different star, the rock in its nucleus, if it has rock, condensed from a different molecular cloud. The chemistry, the isotope ratios, the organic molecules that might be locked inside, all of it is data from somewhere else. And because the object has spent millions or tens of millions of years in interstellar space, exposed to cosmic rays and the cold radiation of the galaxy, it also carries information about the conditions in the space between stars, conditions we can only study indirectly from Earth. Spectroscopy and photometry give us surface data. To really understand what 3I Atlas is made of, someone would have to go there, send a probe, collect a sample, bring it back. That is not happening. Interstellar objects move too fast and appear too suddenly for current mission planning to respond. By the time you design a spacecraft, build it, launch it, and send it on an intercept trajectory, the object is long gone. The European Space Agency studied the possibility of sending a rapid response mission to an interstellar object and concluded it was technically feasible, but only if the mission was designed and built in advance, waiting on standby for a target to appear. No space agency has committed funding to such a mission yet, so for now, Remote observation is all we have. Telescopes on the ground and in orbit, collecting photons, measuring spectra, tracking positions. It is not perfect. It is not even close to what we could learn from a sample return mission, but it is what we can do with the tools we have and the time we have left. By the time 3I Atlas reappears in December, the global network will be ready. Observing schedules are already being updated, proposals are being written, instruments are being calibrated. And somewhere, a graduate student is probably writing code right now to process the data that has not been collected yet. The object is still out there, still moving, still carrying its secrets, and the clock is still ticking. The object was supposed to be simple. A comet from another star system moving through our neighborhood on its way to somewhere else. Survey telescopes spot it, observatories confirm the trajectory, spectroscopes identify water and dust, and everyone writes papers about interstellar chemistry. Clean story, predictable science, box checked. 3I Atlas did not cooperate. The first hint that something was off came from the brightness measurements. When astronomers track a new object, one of the first things they do is measure how bright it appears over time. Plot those measurements on a graph, and you get what's called a light curve. For most objects, the light curve is relatively smooth. It might show a gradual rise and fall as the object moves closer to and farther from the sun, but the day-to-day variations are usually small and predictable. 3I Atlas showed variations that made no sense. The brightness changed erratically over timescales of hours, not by huge amounts. We are talking about fluctuations of maybe 20 or 30%. But those fluctuations were happening too fast and too irregularly to fit the standard models. When a spherical object rotates, its brightness stays mostly constant. A perfect sphere looks the same from every angle, so unless the surface has bright and dark patches, rotation does not change the apparent brightness much. When an elongated object rotates, the brightness varies in a smooth periodic way. As the long axis points toward you, the object looks brighter. As it turns sideways, it dims. The pattern repeats with every rotation. The light curve from 3I Atlas did not show a smooth repeating pattern. It showed something closer to chaos. Some nights the brightness would dip sharply, then recover, then dip again. Other nights it would stay relatively constant. There was no obvious period, no clean sine wave you could fit to the data. It looked less like a rotating object and more like something tumbling. Tumbling happens when an object is spinning around multiple axes at once, instead of rotating cleanly around a single axis like a top. Picture a football wobbling end over end through the air after a bad throw. That kind of motion is unstable and unpredictable, and it produces exactly the kind of messy light curve 3I Atlas was showing. But tumbling typically happens to objects that have been recently disturbed. A collision, a close encounter with a planet, something that knocked the object out of whatever stable rotation it had before. For an interstellar object that has been drifting through empty space for millions of years, tumbling is unusual. Space is mostly empty. There is nothing out there to hit. An object ejected from another star system should have had plenty of time to settle into a stable rotation state long before it arrived here, unless its shape is so irregular that stable rotation is impossible, or unless something happened to it recently that we do not know about. The shape issue became more obvious as more data came in. Astronomers tried to model what kind of object could produce the observed light curve, and the results were uncomfortable. To get brightness variations as large as what was being measured, the object would have to be extremely elongated. We are talking about an axis ratio of at least 5:1, meaning the long dimension is 5 times longer than the short dimension. Some models pushed that ratio even higher, closer to 10:1. For comparison, most asteroids and comets in our solar system are roughly 2-to-1 or 3-to-1 at most. Oumuamua, the first interstellar visitor, was estimated to have an axis ratio of about 6-to-1 or possibly higher, which made it one of the most elongated natural objects ever observed. If 3I Atlas is even more extreme than Oumuamua, we are looking at something that resembles a cigar or a needle more than a rock. That is not impossible. Objects can be elongated, but it raises questions about how they got that way. One possibility is that the object is a fragment, something that used to be part of a larger body, then broke apart, and what we are seeing is a shard. Collisions in the outer regions of planetary systems can shatter comets and asteroids into pieces, and those pieces retain the elongated shapes you would expect from a fracture. Another possibility is tidal forces. If the object passed very close to a massive body, a star or a giant planet, the difference in gravitational pull between the near side and the far side could have stretched it. Tidal disruption events like that are rare, but they happen. The third possibility is that the object formed this way. Some simulations of planetary formation suggest that the earliest generation of planetesimals, the building blocks of planets, could have been highly irregular before collisions ground them down into more spherical shapes. If 3I Atlas is a pristine fragment from the early days of another star system, it might simply look strange because it never had time to round itself out. None of those explanations are fully satisfying because each one requires specific conditions that we cannot confirm. We do not know if the object was involved in a collision. We do not know if it passed close to anything. We do not know how old it is or what stage of planetary formation it represents. We are guessing based on incomplete data and trying to fit the guesses to models that were built using objects from our own solar system. Then the spectroscopy results started coming in and things got stranger. Spectroscopy is supposed to be the part where you get answers. Point a spectrograph at an object, collect its light, spread that light out into a spectrum, and read the chemical fingerprints. Comets have predictable spectra. Water vapor shows up as a series of absorption and emission lines in the near, infrared, and ultraviolet. Carbon monoxide, carbon dioxide, methane, ammonia, all the common ices you expect in a comet, they each have their own signatures. Dust shows up as a broad continuum, a smooth background glow that comes from tiny particles scattering sunlight. If you are looking at a standard comet, you see all of that. Water dominates, dust is present, and you get traces of other volatiles depending on how active the comet is. The first spectra of 3I Atlas showed water. That was expected. The object had been classified as a comet based on the presence of a faint coma detected by Hubble. Comas form when ice on the surface sublimates and releases gas and dust into space. If there is a coma, there is water. The spectroscopic confirmation was routine. What was not routine was everything else that was missing. Carbon monoxide should have been there. Comets from our solar system typically contain significant amounts of carbon monoxide ice, sometimes as much as 10 or 20% by mass. When that ice heats up and sublimates, it produces a strong spectral signature in the millimeter and submillimeter wavelengths that radio telescopes can detect. Several observatories, including the Atacama Large Millimeter Array in Chile, pointed their instruments at 3I Atlas looking for that signature. They did not find it. Or more precisely, they found an upper limit so low that it implied the object contained far less carbon monoxide than any typical comet. Carbon dioxide was also weak or absent. Same story. Standard comets outgas carbon dioxide as they approach the sun. The sublimation temperature for carbon dioxide ice is lower than for water ice, which means it starts outgassing earlier and more vigorously. But the spectroscopic searches for carbon dioxide around 3I Atlas came back with either non-detections or marginal detections that were barely above the noise. If the object contains carbon dioxide, it is not releasing much of it. Methane, ammonia, hydrogen cyanide, the other usual suspects, also missing or too faint to confirm. That left water and dust. And even those signals were weaker than expected for an object at this distance from the Sun, showing a detectable coma. The activity level, meaning the rate at which gas and dust were being released, was low, very low. Lower than comets from the Oort cloud at the same distance, lower than Jupiter family comets, lower than almost any comet that has been studied in detail. So what was going on? The simplest explanation is that 3I Atlas is not very icy. Maybe the surface is covered in a thick layer of dust and refractory material, rocky stuff that does not sublimate, and that layer is insulating the ice beneath it. This is not unheard of. Some comets in our solar system have developed thick mantles of dust over time as repeated passes near the Sun bake off the surface ices and leave behind a crust of non-volatile material. Those comets look dark and inert until something, a meteorite impact or a crack in the crust, exposes fresh ice and triggers a sudden outburst of activity. If 3I Atlas has a mantle like that, it would explain why the spectroscopic signatures are so weak. The ice is there, it is just hidden, but that explanation has problems. Interstellar objects have not been near the Sun before. This is 3I Atlas's first pass through any star system in millions of years. It should not have had time to build up a thick mantle of the kind you see on old, exhausted comets. Unless the mantle formed in its original star system before the object was ejected and has been sitting there ever since, that is possible. Some models of planetary system formation suggest that comets can develop mantles early in their lives if they spend time in the warm inner regions of a protoplanetary disk before being scattered outward. If 3I Atlas formed in such an environment, it might have baked its surface early and retained that crust through its entire journey across interstellar space. Alternatively, the object might just be rocky, not a comet at all in the traditional sense, but an interstellar asteroid, a chunk of silicate or metal with only a trace amount of ice mixed in. Oumuamua raised the same question. It showed no detectable outgassing and no coma, despite passing well within the orbit of Mercury where any significant ice content should have sublimated. Astronomers debated for months whether Oumuamua was a comet that had lost its volatiles or an asteroid that never had them. The debate was never fully resolved because the object faded before anyone could gather enough data. 3I Atlas is not quite as extreme as Oumuamua. It does have a coma, it is outgassing, but the level of activity is so low and the composition so stripped down that calling it a typical comet feels wrong. It is something in between, a hybrid, an object with some ice, some rock, and a composition that does not fit cleanly into the categories we have built from studying solar system objects. There is another possibility that keeps coming up in the literature, and it is the least comfortable one. Maybe the object is not stripped down. Maybe it is just different. Maybe comets from other star systems do not look like comets from ours. Maybe the chemistry, the mix of ices and rock, the ratios of carbon to oxygen to nitrogen, all of it is different because it formed under different conditions around a different star. If that is true, then every interstellar object we detect is going to challenge our models because our models were built from a sample size of one. Our solar system, one star, one protoplanetary disk, one set of initial conditions. We have assumed for decades that planetary formation is roughly universal, that the basic processes of dust sticking together, ice condensing, planets growing, are the same everywhere. And maybe they are, but the details, The specific temperatures and pressures and elemental abundances, those can vary. A star slightly cooler than the Sun would have a different snowline, the distance from the star where water ice can condense. A disk with more carbon and less oxygen would produce different types of ice. A system that formed in a denser part of the galaxy might have been enriched with heavy elements from nearby supernovae, changing the composition of everything that grew there. If 3I Atlas formed in a system like that, its chemistry could be legitimately alien, not in the sense of life or intelligence, but in the sense that the rock and ice it is made from reflect a different starting recipe than anything we have seen before. And if that is the case, we are not going to understand it by comparing it to Halley's Comet or Kuiper Belt objects. We are going to have to build new models from scratch, and we are going to need a lot more data than we currently have. The lack of a visible tail added to the confusion. Comets are famous for their tails, those long glowing streamers that stretch across the sky in historical paintings and etch themselves into the memories of anyone lucky enough to see a bright comet. The tail forms when gas and dust escaping from the nucleus get pushed away from the Sun by radiation pressure and the solar wind. The gas forms one tail, usually bluish and pointing directly away from the Sun. The dust forms another tail, yellowish and curved because the dust particles are heavier and lag behind the gas. Together, the tails can extend for millions of kilometers, making a comet look far larger than it actually is. 3I Atlas, despite being confirmed as an active comet, did not develop a prominent tail. Early images showed a faint coma, a fuzzy glow around the nucleus, but no clear tail structure. As the object moved closer to the Sun and activity should have increased, observers kept watching for a tail to appear. It never did, or more accurately, it remained too faint to see clearly. Some deep images taken with large telescopes hinted at a faint streamer extending away from the nucleus, but nothing like the dramatic tails you see on bright comets like Neowise or Hale-Bopp. The absence of a tail does not necessarily mean the object is not outgassing. Tails only become prominent when the rate of gas and dust production is high enough to create a large, diffuse cloud that reflects enough sunlight to be visible. If the activity level is low, the coma stays small and the tail never develops. That matches what spectroscopy was showing. The object was outgassing, but barely. Just enough to create a faint haze around the nucleus, not enough to produce the kind of tail you could see from Earth without serious optical equipment. Still, it was disappointing. One of the reasons the public gets excited about comets is the tails. They are visually dramatic. They look like something out of a fantasy novel. When astronomers announced that an interstellar comet was passing through the solar system, a lot of people expected a spectacle. What they got was a faint dot that required a telescope to see and looked basically like a slightly fuzzy star. Not exactly headline material. For scientists, the lack of a tail was more interesting than disappointing because it was another data point that did not fit. Comets from the Oort cloud, the distant reservoir of icy bodies that surrounds the solar system, develop visible tails when they fall inward toward the Sun. Those comets are making their first pass through the inner solar system, just like 3I Atlas. They contain pristine ice that has never been heated. When that ice hits sunlight for the first time, it sublimates vigorously, producing bright comas and long tails. If 3I Atlas is also making its first pass through any star system in millions of years, it should behave like a pristine Oort cloud comet. It does not. It behaves like a comet that has been near a star before, or a comet that is mostly rock, or a comet from a system where the ice is compositionally different enough that it does not sublimate the way we expect. Researchers started proposing models to explain the discrepancies. One model suggested the object is a rubble pile, a loose collection of fragments held together by weak gravity. Rubble pile structures are common among asteroids and might be common among comets as well. If 3I Atlas is a rubble pile with a lot of empty space between the fragments, its overall density would be low and its structural integrity would be weak. That could explain the tumbling. Rubble piles do not rotate cleanly because the internal structure shifts and wobbles as the object spins. It could also explain the low outgassing rate. If the object is porous with lots of cracks and voids, heat from the sun might penetrate deeper into the interior, but the escaping gas would have to travel through a maze of passages to reach the surface. That would slow the outgassing and reduce the coma brightness. Another model focused on the surface composition. If the nucleus is covered in a layer of dark, carbon-rich material, similar to what we see on some asteroids and Kuiper Belt objects, it would absorb sunlight efficiently but not necessarily sublimate much ice. That dark layer would heat up, conduct some of that heat to the ice below, but also radiate a lot of it back into space. The result would be modest outgassing and a faint coma, exactly what is observed. This model has the advantage of explaining why the object looks so dark. Early brightness measurements suggested 3I Atlas has a very low albedo, meaning it reflects only a small fraction of the sunlight hitting it. Most comets are relatively dark, with albedos around 4 or 5%, but some measurements of 3I Atlas suggested it might be even darker, closer to 2 or 3%. That is asteroid territory. Carbonaceous asteroids, the dark primitive bodies that make up a large fraction of the main belt, have albedos that low. If 3I Atlas is coated in similar material, it would look more like an asteroid than a comet, even though it is outgassing like a comet. The third model took a different approach. Instead of trying to explain why the object looks strange, it asked whether we are interpreting the data correctly. Light curves can be tricky. If an object has a complex shape with multiple lobes or an irregular surface covered in bright and dark patches, the light curve can look chaotic even if the rotation is stable. Some researchers suggested that 3I Atlas might not be tumbling at all. It might be rotating normally, and what looks like chaos is actually just the combined effect of an irregular shape and a non-uniform surface. This interpretation does not solve the composition problem, but it does make the object seem a little less bizarre. Irregular shapes are common. Non-uniform surfaces are common. If 3I Atlas is just an ordinary comet with a weird shape and a patchy surface, that is easier to swallow than a tumbling interstellar rubble pile with an anomalous composition. The problem with all these models is that they are based on incomplete data. We have light curves, but not from every angle. We have spectra, but only covering a limited range of wavelengths. We have size estimates, but with huge uncertainties. We do not have radar data, which could tell us the object's shape and rotation directly. We do not have high-resolution images showing surface features. We do not have measurements of the nucleus temperature, which would tell us how efficiently it is absorbing and radiating heat. We are trying to solve a puzzle with half the pieces missing, and every piece we do have seems to point in a slightly different direction. That is what baffled researchers. Not that the object was strange. Strange is expected when you are studying something from outside the solar system. What baffled them was that every new measurement made the object harder to explain, not easier. Normally, as you gather more data, the picture gets clearer, uncertainties shrink, models converge. With 3I Atlas, the opposite happened. More data meant more questions. The light curve implied extreme elongation and possibly tumbling. The spectra implied low volatile content and weak activity. The lack of a tail implied either a mantle, low ice content, or unusual ice composition. The dark surface implied carbonaceous material or a mantle of refractory dust. Every observation was internally consistent, but the observations did not fit together into a single coherent story, and the clock kept ticking. By mid-September, the object had moved too close to the Sun to observe safely. It disappeared into the glare, and the first observational window closed. The next chance to study it would come in December, after it swung around the Sun and emerged on the far side. By then, it would be moving away, dimming steadily. The second window would be narrower, the data harder to collect, and the opportunity to answer the outstanding questions would be slipping away with every passing day. Somewhere in the archive of observations already collected, there might be clues that could resolve some of the mysteries. Researchers are still analyzing the data, running simulations, comparing 3I Atlas to other objects. But the truth is, without more observations, many of the questions will remain open. And without a mission to visit the object, to image it up close, to sample its surface or measure its interior, some questions might never be answered. The planetary defense community had already cleared 3I Atlas of any impact risk. The orbit was well understood. The object was not a threat. It would pass Earth at a safe distance, swing around the Sun, and leave the solar system forever. That part of the story was settled. What was not settled, what kept astronomers awake scrolling through data and writing emails to colleagues in other time zones, was the bigger question. What exactly had just passed through our solar system? And what did it tell us about the kinds of objects drifting through the space between stars? The object was cleared. NASA said so. The European Space Agency said so. Every observatory that tracked 3I Atlas through August and September came to the same conclusion. The trajectory was well understood. The closest approach to Earth would be about 170 million miles, roughly 1.8 astronomical units. That is farther than the Sun, much farther. The object was not going to hit us. It was not even going to come close. And yet, the moment the hyperbolic orbit was confirmed, planetary defense systems around the world lit up. Not because anyone thought the object was dangerous, but because anything moving that fast, coming in from that angle, crossing through the inner solar system on a trajectory nobody predicted, fits a profile. The profile of something that could, under different circumstances, end civilization. And when something fits that profile, protocols activate automatically, whether the object turns out to be harmless or not. This is how planetary defense works. It is not a single organization or a single telescope. It is a network, a global collaboration of survey programs, space agencies, university observatories, and tracking systems that were built piece by piece over the last 3 decades to answer one question: are we about to get hit? The answer, most of the time, is no. But the process of arriving at that answer requires watching the sky constantly, calculating orbits precisely, and responding fast when something new shows up. Because the difference between a harmless flyby and an extinction-level impact is often just a few degrees of trajectory. A slight change in angle, a tiny difference in velocity, and an object that was supposed to miss becomes an object that does not. 3I Atlas, despite being an interstellar visitor with no chance of hitting Earth, became a test case, a real-world exercise for a system designed to catch the thing that does not miss. And in the process, it revealed both how far planetary defense has come in the last 20 years and how much work is still left to do. The modern era of planetary defense began on June 30th, 1994. That was the day fragments of comet Shoemaker-Levy 9 slammed into Jupiter. The comet had been torn apart by Jupiter's gravity during a close pass 2 years earlier, and the fragments, 21 of them, fell back into the planet over the course of a week. Each impact released energy equivalent to millions of megatons of TNT. The largest fragment, called Fragment G, hit Jupiter's atmosphere with a force estimated at 6 million megatons. For comparison, the largest nuclear weapon ever detonated, the Soviet Tsar bomber, was 50 megatons. Fragment G was 120,000 times more powerful. The impacts left dark scars on Jupiter's cloud tops that were visible from Earth for months. Some of the scars were larger than the entire diameter of Earth. Astronomers watched the whole thing happen in real time using Hubble, the Galileo spacecraft, and ground-based telescopes around the world. It was the first time in human history that we witnessed a major impact event on another planet. The lesson was obvious. If a comet could do that to Jupiter, a much smaller object could do something catastrophic to Earth. And unlike Jupiter, which gets hit by things all the time because its gravity is so strong, Earth has a much smaller target area. We get hit less often, but when we do, the results are not absorbed harmlessly by a thick atmosphere made of hydrogen and helium. They punch through our thin atmosphere and hit solid ground, or ocean. Either way, the energy release is enough to vaporize cities, trigger tsunamis, ignite wildfires, and throw enough dust into the atmosphere to block out the sun for months or years. The dinosaurs found that out 66 million years ago when an asteroid about 10 kilometers across hit the Yucatan Peninsula in what is now Mexico. The impact triggered a mass extinction that wiped out 3/4 of all species on Earth. The crater called Chicxulub is still there, 180 kilometers across, buried under layers of sediment. The energy release was estimated at 100 million megatons, roughly 2 million Tsar bombers, enough to set forests on fire across entire continents and throw so much debris into the stratosphere that global temperatures dropped by as much as 10 degrees Celsius for years. Smaller impacts happen more often. In 1908, something exploded over Tunguska in Siberia, flattening 80 million trees across 2,000 square kilometers. The object, probably a small asteroid or comet fragment between 50 and 100 meters across, detonated in the atmosphere before it hit the ground. The explosion was estimated at 10 to 15 megatons. No one was killed because the area was remote and sparsely populated. If the same explosion had happened over a city, the death toll would have been in the millions. In 2013, a much smaller object, roughly 20 meters across, exploded over Chelyabinsk, Russia. The airburst released about 500 kilotons of energy, roughly 30 times the yield of the Hiroshima bomb. The shockwave shattered windows across the city, injuring more than 1,500 people. Most of the injuries were from flying glass. The object was not detected before it hit because it came in from the direction of the sun, where ground-based telescopes could not see it. Those three events, Chicxulub, Tunguska, and Chelyabinsk, span a range of scales and consequences. Chicxulub was a mass extinction. Tunguska was a regional catastrophe that happened to occur in an empty forest. Chelyabinsk was a wake-up call, a reminder that even small objects can cause damage and that we are not watching the sky as carefully as we think we are. After Shoemaker-Levy 9, after Tunguska, after Chelyabinsk, governments and space agencies around the world started taking the threat seriously, not because impacts are common, they are not. Large impacts are extremely rare on human timescales, but the consequences of even a moderately sized impact are so severe that the risk, low probability multiplied by high consequence, is worth paying attention to. In 1998, NASA established the Near-Earth Object Program, later renamed the Center for Near-Earth Object Studies. The program's mission was to find and track asteroids and comets that come close to Earth. In 2016, NASA formally created the Planetary Defense Coordination Office, or PDCO, as the central hub for coordinating planetary defense efforts across the agency and with international partners. The office's mandate is straightforward: find objects that might hit us, track them, figure out their orbits, and if one of them is on a collision course, develop options for dealing with it. The first step is detection. You cannot defend against something you do not know is there. That means surveying the sky constantly, looking for anything that moves. Near-Earth objects, or NEOs, are defined as asteroids or comets that come within about 50 million kilometers of Earth's orbit. Not all NEOs are dangerous. Most of them are small, and most of them never come particularly close to Earth. But a subset of NEOs, called potentially hazardous objects, or PAOs, are large enough and close enough that they warrant extra attention. A PAO is defined as an object larger than about 140 meters across that comes within about 7.5 million kilometers of Earth's orbit. 7.5 million kilometers sounds like a lot. It is about 20 times the distance from Earth to the Moon. But on astronomical scales, it is close, and orbital mechanics being what they are, an object that passes that close on one orbit could, depending on gravitational interactions with Earth or other planets, end up on a collision course on a future orbit. So PATOs get tracked carefully. Their orbits are calculated and recalculated. Their future positions are predicted decades or even centuries into the future. And if the predictions show a small but non-zero chance of impact, the object gets flagged for further study. As of late 2025, astronomers have identified more than 36,000 near-Earth objects. About 2,500 of them are classified as potentially hazardous. Of those, exactly 0 are currently on a trajectory that will hit Earth in the foreseeable future. That could change. New objects are discovered every week, and known objects occasionally turn out to have orbits that are less well understood than initially thought. But right now, today, there is no asteroid or comet on NASA's tracking list that poses a credible impact threat within the next century. 3I Atlas does not fit the PAO definition because it is not going to come anywhere near the 7.5 million kilometer threshold. Its closest approach to Earth is more than 20 times farther away than that. It is also not going to stick around. PAOs are typically objects on elliptical orbits that bring them back into the inner solar system repeatedly over thousands or millions of years. Those repeated passes are what make them potentially hazardous. Given enough time and enough orbits, gravitational interactions with planets can nudge an object onto a collision course. 3I Atlas is on a hyperbolic trajectory. It is making one pass through the solar system and leaving forever. There is no future orbit to worry about, no chance of a return visit, no long-term risk. And yet, when the Atlas Survey Telescope in Chile detected the object and flagged its unusual velocity, the alert went out to the same network that tracks PAOs, because the detection systems do not wait to classify an object before sounding the alarm. If something is moving fast and it is in or near Earth's orbital neighborhood, the systems alert first and ask questions later. Within hours of the initial detection, NASA's Center for Near-Earth Object Studies at the Jet Propulsion Laboratory began calculating the orbit. They used data from Atlas, combined with follow-up observations from other telescopes, to refine the trajectory. The software that does this is called Scout. It is designed to automatically calculate orbits for newly detected objects and assess whether they pose any near-term impact risk. Scout runs constantly, processing data from survey telescopes around the world, flagging anything that looks even remotely threatening. For 3I Atlas, Scout calculated the hyperbolic orbit almost immediately. The eccentricity, a number that describes how stretched out an orbit is, came back greater than 1. Anything with an eccentricity above 1 is on an open trajectory. It is not bound to the Sun. It is not coming back. That single number told Scout and the researchers monitoring Scout's output that this was not a PHO, it was something else, an interstellar interloper. Harmless, at least in terms of collision risk, but scientifically fascinating. The distinction between a PHO and an interstellar object might seem academic. Both are rocks or ice balls moving through space. Both are detected by the same telescopes using the same techniques, but the difference matters because the response is completely different. If an object is identified as a PHO, especially one with a non-zero chance of hitting Earth, the response involves more than just tracking. It involves modeling the impact consequences. Where would it hit? How much energy would it release? What kind of damage would it cause? Those questions feed into a larger decision-making process that considers options for deflection or mitigation. If an object is identified as an interstellar visitor, the response is purely scientific. Track it, measure it, learn from it. There is no deflection planning because there is no threat. The object is already moving away, and nothing we could do would change its trajectory in a meaningful way. Even if we wanted to, which we do not, launching a mission to intercept an object moving at 61 kilometers per second relative to the Sun is beyond current technology. By the time you built the spacecraft and got it into position, the object would be long gone. That does not mean 3I Atlas was irrelevant to planetary defense. On the contrary, it provided a real-world test of the detection and tracking systems. Did the surveys spot it early enough? Yes. Atlas detected the object when it was still far enough away that there was plenty of time to refine the orbit and confirm it was not a threat. Could the tracking network calculate the trajectory accurately? Yes. Within days, multiple observatories had confirmed the hyperbolic orbit and ruled out any possibility of an Earth impact. Did the alert systems work? Yes. The detection triggered the appropriate notifications, and researchers around the world were able to respond quickly. In short, the system did exactly what it was supposed to do. And that is valuable information, because the next time an object shows up moving that fast, it might not be an interstellar visitor on a safe trajectory. It might be a long-period comet from the Oort cloud on a collision course. And when that happens, the response has to be fast and accurate. There is no time for meetings and committee reviews. You need the detection, the tracking, the orbital calculation, and the impact assessment to happen in hours or days, not weeks or months. The possibility of a comet impact is one of the harder problems in planetary defense. Asteroids are relatively predictable. Most of them live in the main belt between Mars and Jupiter, and the ones that cross Earth's orbit do so on well-understood trajectories that do not change much over time. Comets are messier. Long-period comets, the ones that come from the Oort cloud, spend most of their time far from the Sun, where they are invisible to telescopes. They only become detectable when they fall inward and start to heat up. By that point, they are already moving fast, and there may be only months or even weeks of warning before closest approach. Worse, comets can outgas unpredictably. As the ice on their surface sublimates, it releases jets of gas that act like tiny rocket engines, pushing the comet slightly off its predicted path. That makes long-term trajectory predictions unreliable. An asteroid's orbit, once calculated, stays accurate for decades or longer. A comet's orbit can change from week to week depending on how active it is. 3I Atlas demonstrated all of those challenges. It was detected relatively late, after it had already crossed the inner solar system boundary. Its activity level changed over time, making photometric measurements tricky. And its trajectory, while ultimately confirmed to be hyperbolic and safe, required multiple observations from multiple sites to pin down with confidence. If the object had been on a slightly different path, one that brought it closer to Earth, the same uncertainties would have made impact prediction much harder. That brings us to the question of what you actually do if an object is on a collision course. The answer depends on how much warning you have. If you have years or decades of warning, the preferred option is a kinetic impactor. That is a fancy name for a very simple idea. You build a spacecraft, launch it toward the asteroid, and ram it at high speed. The impact transfers momentum to the asteroid, changing its velocity by a small amount. That small change, given enough time, shifts the asteroid's orbit enough that it misses Earth instead of hitting. This is not science fiction. In September 2022, NASA successfully tested this technique with a mission called DART, the Double Asteroid Redirection Test. DART was a small spacecraft about the size of a vending machine that was launched toward a binary asteroid system called Didymos. The target was Dimorphos, a small moon about 160 meters across orbiting the larger asteroid Didymos. DART slammed into Dimorphos at over 6 kilometers per second. The impact changed Dimorphos's orbital period by 32 minutes, far more than the minimum 5-minute change that NASA had set as the success threshold. The DART mission proved that kinetic impactors work. If we detect an asteroid with enough lead time, we can deflect it. The key phrase is enough lead time. If you only have months or a few years of warning, a kinetic impactor might not be enough. The velocity change you can impart with a single spacecraft is small. It takes time for that small change to accumulate into a large change in position. If the asteroid is already close and moving fast, you might not have that time. In that scenario, the next option is a gravity tractor. This is a slower, gentler approach. Instead of hitting the asteroid, you park a spacecraft near it and let the spacecraft's gravity pull on the asteroid. The pull is tiny. The spacecraft weighs maybe a ton. The asteroid weighs millions or billions of tons. But gravity works both ways. The spacecraft pulls on the asteroid, and the asteroid pulls on the spacecraft. If you keep the spacecraft hovering near the asteroid for months or years, the cumulative gravitational tug can shift the asteroid's orbit just enough to change a hit into a miss. Gravity tractors require a lot of time. They are not an option for short warning scenarios, but they have one advantage over kinetic impactors. They are precise. A kinetic impactor changes the asteroid's velocity suddenly, and the exact size of the change depends on details like the asteroid's internal structure, which we often do not know. A gravity tractor changes the velocity gradually and predictably. You can measure the effect in real time and adjust the spacecraft's position to fine-tune the deflection. If you have very little warning, days or weeks instead of years, the options get grim. At that point, you are not deflecting the asteroid. You are trying to minimize the damage. That might mean evacuating the impact zone if it is on land, or bracing for a tsunami if it is in the ocean. It might mean hardening critical infrastructure, stockpiling supplies, or preparing for a long-term disruption of agriculture and climate if the object is large enough. There is one other option that comes up occasionally in discussions of planetary defense, and it is the option nobody wants to talk about seriously: nuclear weapons. A nuclear explosion near an asteroid, not on the surface but detonated at a distance, could in theory vaporize a layer of surface material. The expanding vapor would act like a rocket exhaust, pushing the asteroid in the opposite direction. The physics works, the engineering is feasible, but the political and logistical complications are enormous. Launching a nuclear weapon into space requires international agreements and coordination that would take years to negotiate under normal circumstances. In an emergency with an asteroid on a collision course, the timeline would be compressed to months or weeks. And even if you could get a nuclear device to the asteroid in time, you would need extremely precise detonation timing to push the asteroid in the right direction. A mistake could break the asteroid into fragments, turning one impact into multiple impacts. For all these reasons, nuclear deflection is considered a last resort. Something to consider only if every other option has failed, or if the warning time is so short that nothing else will work. None of these deflection techniques would have been relevant for 3I Atlas. The object was not on a collision course. It was not a threat, but the fact that planetary defense systems tracked it, calculated its orbit, and confirmed it was safe is exactly the point. The systems are designed to work automatically, to respond to any object that might pose a risk, and to deliver a clear answer as quickly as possible. The psychological dimension of this cannot be ignored. When news broke that an interstellar object was passing through the solar system, moving at 137,000 miles per hour, the public reaction was immediate. Social media filled with speculation. Was it dangerous? Could it hit Earth? Should we be worried? Some of the speculation was reasonable, most of it was not. Conspiracy theories about alien spacecraft and rogue planets circulated alongside the actual science. News outlets ran headlines that emphasized the speed and the interstellar origin without always making it clear that the object was going to miss Earth by more than 100 million miles. NASA and other space agencies responded with clear, factual statements. The object is not a threat. It will not come close to Earth. There is no danger. Those statements were accurate and unambiguous, but the fact that they had to be issued at all points to a broader problem. Public understanding of orbital mechanics, of what constitutes a close approach versus a collision course, is limited. When people hear that something is passing through the solar system at 100,000 miles per hour, the instinctive reaction is alarm. Speed sounds dangerous. The context that everything in the solar system is moving at high speeds relative to something else gets lost. This is one of the ongoing challenges for planetary defense, communicating risk accurately without causing panic. The goal is not to reassure people that there is no danger ever. There is danger. Asteroids and comets hit Earth. The question is whether a specific object, detected at a specific time, poses a specific threat. For 3I Atlas, the answer was no. Clearly, definitively no. But getting that message across required not just calculating the orbit, but explaining what the orbit meant in terms that non-specialists could understand. The broader context is that planetary defense is still a young field. The first comprehensive surveys of near-Earth objects only started in the late 1990s. Before that, we had no idea how many objects were out there or how often they came close. Now, 3 decades later, we have catalogued tens of thousands of objects. We have tested deflection techniques. We have built international coordination frameworks. We have, for the first time in history, a realistic chance of detecting an incoming asteroid or comet with enough warning to do something about it. But the job is not finished. The surveys are not complete. There are still thousands of objects out there that have not been found yet. Some of them are small, Tunguska-sized objects that are hard to detect but could still cause regional devastation. Some of them are comets on long-period orbits that have not passed through the inner solar system in recorded history, and some of them might be on trajectories that current models do not predict. 3I Atlas, in its brief pass through the solar system, served as a reminder that space is full of surprises. Objects appear without warning, trajectories defy expectations, and the systems we have built to protect the planet are constantly being tested by the universe itself. The next object might not be an interstellar visitor on a harmless flyby. It might be a comet from the Oort cloud, detected with months of warning, on a trajectory that passes uncomfortably close to Earth. Or it might be a small asteroid that nobody saw coming until it was too late. Either way, the response will depend on the same detection networks, the same tracking systems, the same orbital calculations that processed 3I Atlas and confirmed it was not a threat. The difference next time might be that the answer is yes instead of no. And when that happens, everything we have learned from tracking objects like 3I Atlas, every refinement of the detection algorithms, every improvement in orbital prediction software, every test of the coordination networks will matter, because the stakes are not abstract, they are planetary, and the clock, as always, will be ticking. The problem with tracing a comet's path backward through space is that space does not hold still. The stars move, the sun moves, the galaxy rotates, and by the time you have rewound the trajectory far enough to figure out where something came from, the address you are looking for is no longer there. That is the situation astronomers find themselves in with 3I Atlas. They know where it is. They know where it is going. They even know, with remarkable precision, the shape of the curve it is following through the solar system. What they cannot tell you, at least not yet, is where it started, not which star, not which planetary system, not even which general neighborhood of the Milky Way, beyond a vague gesture toward Sagittarius and the crowded mess of stars near the galactic center. The trajectory itself is clean, hyperbolic, unambiguous. That word, hyperbolic, carries specific weight in orbital mechanics. It does not mean exaggerated or dramatic, though the internet has certainly made it sound that way. It means the path is open, the object is not in orbit, it came in, it is swinging around, and it is leaving. The mathematical shape of that path is a hyperbola. One branch of the conic sections you might vaguely remember from high school math. Circles, ellipses, parabolas, hyperbolas, all of them describe possible trajectories for objects moving under the influence of gravity. Most things in the solar system move on ellipses: planets, asteroids, comets, even artificial satellites. An ellipse is a closed loop. The object goes around, comes back, goes around again. The sun sits at one focus of the ellipse, and gravity keeps the object tethered. The eccentricity of the ellipse, a number between 0 and 1, tells you how stretched out the loop is. 0 is a perfect circle. Numbers closer to 1 are long, skinny ellipses. Earth's orbit has an eccentricity of about 0.017, nearly circular. Halley's Comet, which swings out past Neptune and then dives back in near the Sun every 76 years, has an eccentricity of about 0.967, still less than 1, still a closed loop. When the eccentricity hits exactly 1, the trajectory becomes a parabola. The object comes in from infinity, swings around the Sun, and heads back out to infinity, but just barely. It is the boundary case between bound and unbound. Parabolic orbits are rare in practice because hitting that exact threshold requires precise conditions that nature does not usually arrange. Most real objects fall on one side or the other. When the eccentricity exceeds 1, you get a hyperbola. The object is moving too fast for the Sun's gravity to hold it. It comes in, bends around, and shoots back out, never to return. The path is open at both ends. That is what 3I Atlas is doing. Its eccentricity is greater than 1. By how much, the published data does not say precisely, but the fact that the hyperbolic shape was recognized within days of discovery means it was not a borderline case. The object was moving fast enough that the shape of the trajectory left no room for doubt. Calculating that trajectory is harder than it sounds. You do not just point a telescope at an object, measure where it is, and plug the numbers into an equation. You measure where it appears to be from Earth, which is itself moving. You correct for the fact that light takes time to travel, so you are seeing the object where it was, not where it is. You account for the fact that your telescope is not sitting at the center of the Earth but on the surface, which means parallax, the apparent shift in position caused by observing from different locations, matters if you are trying to be precise. Once you have a position, you wait a few hours or a few days and measure again. Now you have two positions separated by time. That gives you direction and speed, sort of. Except the object is not moving in a straight line. It is moving under the influence of the sun's gravity and possibly the gravity of nearby planets, and you are observing it from a platform that is also moving under the influence of the sun's gravity. So the motion you see is the combination of the object's real motion and your own motion, and disentangling the two requires math. The standard approach is to fit an orbit. You assume the object is following one of the conic section paths, circle, ellipse, parabola, or hyperbola, and you try to find the orbital parameters that best match the observations. There are 6 parameters: the semi-major axis, which describes the size of the orbit, the eccentricity, which describes the shape, the inclination, which describes the tilt of the orbital plane relative to Earth's orbit, the longitude of the ascending node, which describes where the orbital plane crosses Earth's orbital plane, the argument of perihelion, which describes where the closest approach to the Sun occurs along the orbit, and the time of perihelion passage, which tells you when the object reaches that closest point. For 3I Atlas, early observations gave rough values for all 6 parameters. The semi-major axis for a hyperbolic orbit is technically negative, a mathematical quirk that reflects the fact that the orbit is open rather than closed. The eccentricity was clearly greater than 1. The inclination was steep, meaning the object was not coming in along the plane where most planets orbit. It was diving in from above or below, cutting through the solar system at an angle. The argument of perihelion and the longitude of the ascending node described the orientation of that tilted path, and the time of perihelion passage was predicted for late October 2025, when the object would reach its closest point to the Sun at about 1.4 astronomical units. Each new observation refines the parameters. The first few measurements pin down the rough shape of the orbit, but leave a lot of uncertainty in the details. Add more measurements, and the uncertainties shrink. The semi-major axis becomes more precise. The eccentricity gets nailed down to a tighter range. The predicted time of perihelion shifts by hours or minutes instead of days. This process of refinement continues for as long as the object is visible and moving measurably against the background stars. For 3I Atlas, the refinement process was fast because the object was moving so quickly. Fast motion means large changes in position between observations, which makes the orbit easier to fit. Slower objects, the ones that drift lazily across the sky over weeks or months, require more time to accumulate enough data to distinguish between similar orbital solutions. 3I Atlas gave astronomers clean, unambiguous motion from the start. One of the tools NASA uses for this is called Scout. It is an automated system that takes observations from survey telescopes like Atlas and Pan-STARRS, calculates preliminary orbits, and assesses whether the object might pose an impact risk. Scout does not wait for humans to review the data. It processes observations in near real time, updating its calculations every time new data comes in. For newly discovered objects, Scout can produce an initial orbit estimate within minutes of receiving enough observations. That initial estimate is rough, but it is usually good enough to tell you whether the object is on a closed orbit or an open one, and whether it is coming anywhere near Earth. For 3I Atlas, Scout flagged the hyperbolic trajectory almost immediately. That triggered alerts to the broader astronomical community, and within hours, observatories around the world were collecting follow-up observations. Those observations were fed back into Scout and other orbital calculation software, progressively tightening the uncertainties until the orbit was well enough understood to make confident predictions about the object's future path. The precision required for this is absurd. Positions are measured in arc-seconds, units so small that 1 arc-second is the apparent width of a dime seen from about 4 kilometers away. For an object moving at 61 kilometers per second relative to the Sun, an error of even a fraction of an arc-second in position translates into an error of thousands of kilometers in the predicted location days or weeks later. To get the orbit right, you need dozens of observations from multiple telescopes, all cross-checked against each other to filter out random errors and systematic biases. One source of error is the object's brightness. Faint objects are harder to pinpoint precisely because their light is spread out over multiple pixels on the detector, and the exact center of that smudge is ambiguous. Brighter objects give sharper positions, but brightness depends on distance, surface reflectivity, and whether the object is actively outgassing and producing a coma. 3I Atlas is faint, not impossibly faint, but faint enough that getting precise astrometry required large telescopes with excellent tracking systems and long exposure times. Another source of error is atmospheric distortion. Ground-based telescopes look through kilometers of air, and that air is never perfectly still. It shimmers and shifts, blurring the images. Adaptive optic systems can correct for some of that blurring in real time, but not all of it. The best astrometric measurements come from space-based telescopes like Hubble, which do not have to deal with the atmosphere. Hubble was pointed at 3I Atlas in late August, confirming the presence of a faint coma and refining the astrometric position with precision that ground-based telescopes could not match. Once the orbit is well understood, the next question is whether it is being influenced by anything other than gravity. For most asteroids, gravity is the only force that matters. The object moves under the influence of the Sun and, to a much smaller extent, the planets. The trajectory is predictable. You can calculate where the object will be years or decades into the future, and barring a collision with something else, your prediction will be accurate. Comets are different. Comets outgas. As they warm up near the Sun, ice on their surface sublimates, turning directly from solid to vapor without passing through a liquid phase. That vapor escapes into space, carrying dust with it. The escaping gas acts like a rocket exhaust, pushing the comet slightly off its gravitational trajectory. This is called non-gravitational acceleration, and it is one of the most annoying aspects of comet orbit prediction. The effect is small. For a typical comet, the non-gravitational acceleration might change its velocity by a few meters per second over the course of weeks or months. That sounds negligible. It is not. A change of a few meters per second, sustained over time, can shift the comet's position by thousands of kilometers. That shift shows up in the observations as a deviation from the predicted path. If you calculate an orbit assuming only gravity and then compare it to where the comet actually is, you find a mismatch. The comet is slightly ahead of or behind where it should be. To account for this, astronomers add extra terms to the orbital equations. These terms model the outgassing as a force that depends on how close the comet is to the Sun and how active its surface is. The models are empirical, meaning they are based on observations of how comets actually behave rather than a detailed understanding of the physics of sublimation and gas flow. You fit the non-gravitational terms to the data the same way you fit the orbital parameters, by adjusting the numbers until the calculated path matches the observed path as closely as possible. For 3I Atlas, the question of non-gravitational acceleration is still open. The object is outgassing. Hubble confirmed the presence of a coma, which means gas and dust are escaping from the nucleus. That should produce a measurable non-gravitational force. But whether that force is large enough to affect the orbit significantly and whether astronomers have collected enough data to measure it is not clear yet. The object is faint, the observations are noisy, and the deviations you are looking for are small. It might take months of analysis after the object has moved far enough along its trajectory that any deviations become obvious before the non-gravitational terms can be pinned down. This is where 3I Atlas starts to look like Oumuamua all over again. Oumuamua, the first interstellar visitor, also showed non-gravitational acceleration. The deviation was detected by multiple teams using data from Hubble and ground-based telescopes. The acceleration was small, but statistically significant. It was real. The problem was that no one could find the outgassing that should have caused it. Comets outgas visibly. They produce comas, clouds of gas and dust that glow in reflected sunlight and can be detected spectroscopically. Oumuamua had no coma, no detectable water vapor, no carbon monoxide, no dust. Searches using some of the most sensitive instruments on Earth came back empty. If Oumuamua was outgassing, it was doing so at a level far below what any comet in the solar system produces under similar conditions. That left astronomers with a mystery. The object was accelerating, but the usual explanation for cometary acceleration did not fit. Several alternative explanations were proposed. One was that Oumuamua was outgassing something other than water. Molecular hydrogen, for example, which would be harder to detect because it does not produce strong spectral lines in the wavelengths most telescopes observe. Another was that the object had a highly reflective surface and was being pushed by sunlight itself, a phenomenon called radiation pressure. If the object was extremely lightweight and had a large surface area relative to its mass, radiation pressure could produce measurable acceleration. That explanation led to speculation about light sails and artificial objects, ideas that made headlines but found little support in the scientific community. The most conservative explanation, and the one that most researchers settled on, was that Oumuamua was outgassing at a very low level, just below the detection threshold of the instruments used to search for it. Maybe the ice was buried under a thick layer of dust. Maybe the outgassing was happening in discrete jets pointed away from Earth, so the gas never crossed our line of sight. Maybe the composition was unusual, with ices that sublimate at different temperatures than the water and carbon monoxide we are used to seeing in solar system comets. Any of those scenarios could explain why the outgassing was invisible while still producing enough force to cause the observed acceleration. The point is, non-gravitational acceleration in interstellar objects is not a settled question. It is a clue, a data point that tells you something about the object's composition and activity, but it is not a simple clue. It comes wrapped in ambiguities and measurement uncertainties, and it forces you to confront the possibility that objects from other star systems might not behave the way objects from our own system behave. For 3I Atlas, if non-gravitational acceleration is detected, the first question will be whether it matches the models for cometary outgassing. If it does, that tells you the object is a relatively normal comet, just one that formed somewhere else. If it does not, if the acceleration is too large or too small, or points in a direction that does not match the sun's heating, then you are back to trying to explain an anomaly. And anomalies, as Oumuamua demonstrated, can take years to sort out. The other side of the trajectory question is where the object came from. not in the immediate past, meaning the angle it approached from, but in the deep past, meaning which star system it might have originated in. This is harder than it sounds because space is not static. The stars move, the sun moves, the galaxy rotates. If you want to trace a trajectory backward through time, you have to account for all of that motion. The sun is moving through the galaxy at about 220 kilometers per second, circling the galactic center in a slow, nearly circular orbit that takes about 230 million years to complete. The nearby stars are also moving, each on its own orbit, some moving in roughly the same direction as the sun, others moving at different speeds or angles. When an interstellar object passes through the solar system, its incoming velocity is measured relative to the sun. To figure out where it came from, you subtract the sun's motion and calculate what the object's velocity would be relative to the local standard of rest, a reference frame that accounts for the average motion of stars in the solar neighborhood. For 3I Atlas, that calculation points the incoming trajectory roughly towards Sagittarius, in the direction of the galactic center. That does not mean the object came from the galactic center, which is 26,000 light-years away. It means the direction, when you account for the sun's motion and the rotation of the galaxy, points that way. The object could have come from a star system a few hundred light-years away, a few thousand light-years away, or anywhere along that line of sight. The problem is that the object has been traveling for a long time. If it has been moving at 61 kilometers per second, relative to the local standard of rest, which is close to the average speed of stars in the solar neighborhood, it covers about 1 light-year every 5,000 years. If it came from a star system 500 light-years away, it has been traveling for 2.5 million years. If it came from 1,000 light-years away, 5 million years. During that time, the stars have moved. The star it came from is no longer where it was when the object left, and we do not know which star it came from in the first place, so we do not know how to correct for that star's motion. Astronomers have tried to backtrack the trajectories of both Oumuamua and Borisov, the first two interstellar visitors, using catalogues of stellar positions and velocities from missions like Gaia, which has mapped the positions and motions of more than 1 billion stars in the Milky Way. For Oumuamua, the incoming trajectory pointed roughly toward the constellation Lyra, near the bright star Vega. But when researchers traced the path backward and accounted for stellar motions, they found that Vega was not in that part of the sky 300,000 years ago, which is roughly how long it would have taken Oumuamua to travel from Vega if it had been ejected from that system. The alignment was a coincidence. Oumuamua did not come from Vega. It probably did not come from any star we can name. For Borisov, the origin search was equally inconclusive. The trajectory pointed toward Cassiopeia, but no specific star in that region stood out as a likely source. The object could have come from a red dwarf too faint to show up in catalogues, or from a system that was ejected from a star cluster millions of years ago and has since dispersed. For 3I Atlas, the same difficulties apply. The trajectory points toward Sagittarius, but Sagittarius is crowded. The line of sight passes through the galactic plane, where stars are densest. Thousands of stars lie along that direction, and we do not have accurate motion data for all of them. Even if we did, the travel time is long enough that small errors in stellar velocities would propagate into huge uncertainties in past positions. Tracing the object back to a specific star would require not just knowing where every star is now, but where every star was millions of years ago. We do not have that data. We might never have that data. So the best we can do is describe the origin in probabilistic terms. The object came from somewhere in that general direction. It was likely ejected from a planetary system during the chaotic phase of planet formation, when giant planets were migrating inward or outward and scattering smaller bodies into the outer reaches of the system or flinging them into interstellar space entirely. The same process that built the Oort cloud around our Sun has probably built similar clouds around other stars, and some fraction of the objects in those clouds get ejected rather than remaining bound. Once ejected, they drift through the galaxy for millions or tens of millions of years until, by pure chance, they pass close enough to another star to be noticed. One way to narrow down the origin is to look at the object's composition. If 3I Atlas turns out to have a chemical signature that matches a specific type of star, that could point toward the kind of system it came from. Stars with different masses and ages produce different mixes of heavy elements, and those mixes get incorporated into the planets and comets that form around them. A comet from a young hot star might be enriched in carbon or nitrogen compared to a comet from an old cool star. A comet from a metal-rich star, one that formed later in the galaxy's history when supernova had already enriched the interstellar medium with heavy elements, might have different isotope ratios than a comet from a metal-poor star. Spectroscopy can measure some of those differences, but only if the object is bright enough and active enough to produce strong spectral lines. For 3I Atlas, the faint outgassing and low activity level make detailed compositional analysis difficult. The water signature is there, but the other volatiles, the ones that would give more specific clues about the formation environment, are either missing or too weak to measure confidently. That leaves the origin question open. There is one other possibility that keeps coming up in discussions of interstellar objects, and it is the idea that has generated the most public attention and the most scientific skepticism in roughly equal measure. The possibility that some of these objects are not natural, that they are artificial, probes or debris from another civilization. The idea is not as absurd as it sounds. If other civilizations exist in the galaxy, and if they have developed technology capable of interstellar travel or communication, then artifacts from those civilizations might be drifting through space. Derelict spacecraft, discarded stages of propulsion systems, even intentional probes designed to explore other star systems. The galaxy is old enough and large enough that even a modest rate of artifact production could, over billions of years, fill interstellar space with objects that are not naturally occurring rocks or ice balls. The argument was made most prominently by Avi Loeb, a Harvard astrophysicist, in the context of Oumuamua. Loeb pointed out that Oumuamua's extreme elongation, its lack of visible outgassing, and its non-gravitational acceleration were all anomalies that did not fit standard comet models. He suggested that one explanation, not the only explanation but a possible one, was that the object was a light sail, a thin reflective sheet designed to be pushed by starlight. If the object was artificial, the anomalies would make sense. Light sails are elongated by design. They do not outgas because they are not made of ice, and they accelerate under radiation pressure without needing rocket engines. The scientific community largely rejected that hypothesis, not because it was impossible, but because it invoked an explanation that required far more assumptions than the alternatives. Natural explanations, comets with unusual compositions or hidden outgassing, might be complicated, but they do not require the existence of alien civilizations. Occam's razor, the principle that simpler explanations are usually correct, pointed away from the artificial hypothesis. For 3I Atlas, the same argument applies. The object behaves like a comet. It has a coma. It is outgassing water. Its trajectory can be explained entirely by gravitational forces, possibly with a small non-gravitational term from outgassing. There is nothing about it that screams artificial. That does not mean it is impossible. It just means the evidence is not there. The broader point is that tracing trajectories and calculating orbits can only tell you so much. They tell you where the object is and where it is going. They tell you whether it is bound to the sun or escaping. They tell you, with varying degrees of certainty, the general direction it came from. But they do not tell you what the object is, where it formed, or what system it came from. Those questions require spectroscopy, compositional analysis, and ultimately a lot more data than we currently have. For 3I Atlas, the trajectory is well understood. The orbit is hyperbolic. The path is clear, but the object itself remains, in most of the ways that matter, a mystery. And as it fades from view, moving outward into the dark on a trajectory that will carry it into interstellar space and keep it there forever, it carries those mysteries with it. The next interstellar object will bring new questions, new trajectories to calculate, new orbits to refine, and new reminders that the galaxy is full of things we do not understand, moving through spaces we have barely begun to explore. So here is what we are actually talking about when we say interstellar object. We are not talking about a rock that wandered into the solar system by accident. We are talking about a sample, a physical piece of another star system. Material that condensed out of a protoplanetary disk that formed around a star we cannot name, in a region of the galaxy we might never visit, under conditions we can only guess at. That material spent billions of years locked in orbit around that star, or was ejected early and has been drifting through the void ever since. And now it is here, close enough that we can point instruments at it and measure what it is made of. That is not a small thing. For the entire history of astronomy, we have studied other star systems from a distance. We look at their light, we measure their spectra, we watch planets pass in front of them and infer the size and composition of those planets from the tiny dips in brightness. We build models of how stars form, how planets assemble, how solar systems evolve, and all of those models are constrained by one enormous limitation. We only have one example to work from: ours. Every rock we have ever picked up, every meteorite that has landed on Earth, every sample returned by a space mission, all of it came from our solar system. The moon rocks brought back by Apollo, the comet dust collected by Stardust, the asteroid samples returned by Hayabusa and OSIRIS-REx, they are all pieces of the same story. The story of how our system formed 4.5 billion years ago from a collapsing cloud of gas and dust in this particular corner of the Milky Way. That story is useful. It tells us a lot about planetary formation in general, but it is still just one data point, one example, one recipe. Interstellar objects are the first opportunity we have ever had to hold material from a different recipe. To measure the isotope ratios, the mineral composition, the organic chemistry of something that did not form here. If the chemistry matches ours, that tells us something important. It means the basic processes of planetary formation are universal. The same ingredients, the same physics, produce the same results everywhere. If the chemistry does not match, that is even more interesting. It means conditions in other star systems can be different enough to leave a measurable fingerprint in the material that forms there. For 3I Atlas, the early spectroscopic data showed water. That was expected. Water is common. Hydrogen and oxygen are two of the most abundant elements in the universe, and water ice is stable in the cold outer regions of any planetary system. Comets in our solar system are full of it. Comets in other systems should be full of it too. The detection of water in 3I Atlas does not tell us anything shocking. It tells us that the system this object came from had water, which is not surprising. What is more interesting is what else was or was not there. Carbon monoxide, carbon dioxide, methane, ammonia. The other volatiles that make up the bulk of cometary ice in our system were either missing or present at much lower levels than expected. That could mean the object is unusually depleted in those compounds, or it could mean the object formed in a part of its home system where those compounds did not condense, or it could mean something about the thermal history of that system, the way the protoplanetary disk cooled and the distances at which different ices became stable was different from ours. The snow line is the distance from a star where water ice can condense. Inside the snow line it is too warm. Water stays in vapor form. Outside the snow line it freezes. The location of the snow line depends on the star's luminosity. A hotter, brighter star pushes the snow line farther out. A cooler, dimmer star pulls it closer in. If 3I Atlas formed around a star that was cooler than our Sun, its snow line would have been closer to the star, and the temperature gradient across the disk would have been different. That could change the mix of ices that ended up in the outer reaches of the system where comets form. There is also the question of metallicity. That word does not mean metal in the everyday sense. In astronomy, anything heavier than helium is called a metal. Carbon, oxygen, nitrogen, iron, silicon, all metals. Stars that formed early in the galaxy's history, when there had been fewer supernovae to enrich the interstellar medium with heavy elements, have low metallicity. Stars that formed more recently from gas that had been enriched by multiple generations of supernovae have higher metallicity. The metallicity of the star affects the composition of everything that forms around it. Planets, asteroids, comets, all of them inherit the chemical signature of the protoplanetary disk they condensed from, and that disk inherits its composition from the star. If 3I Atlas came from a low metallicity system, its rock and ice would contain fewer heavy elements than objects from our solar system. If it came from a high metallicity system, the opposite. Measuring those differences requires detailed spectroscopy and ideally a sample return mission. Neither of those is happening for 3I Atlas. The object is too faint, too far away, and moving too fast. What we can measure is limited to the brightest spectral lines and the overall activity level. The detailed chemistry, the isotope ratios, the trace elements, those are out of reach for now. But even the limited data we do have is valuable because it adds to a growing data set. 3 confirmed interstellar objects in less than a decade. Oumuamua in 2017, Borisov in 2019, 3I Atlas in 2025. Each one is different. Each one adds a new piece to the puzzle. Oumuamua was dark, elongated, showed no visible outgassing, and accelerated in a way that did not fit standard comet models. Borisov looked like a normal comet, with a visible coma, a tail, and spectroscopic signatures of water and carbon monoxide that matched comets from our own system. 3I Atlas is somewhere in between. It has a coma, it is outgassing, but the activity level is low, the composition is stripped down, and the light curve suggests an irregular shape or tumbling motion that complicates interpretation. 3 objects, 3 different stories. That diversity tells us something. It tells us that interstellar space is not filled with one type of object. There is variety out there. Some interstellar visitors are icy comets that look and behave like the comets we are used to. Some are rocky, inert bodies that resemble asteroids. Some are hybrids or anomalies that do not fit cleanly into either category. That variety mirrors what we see in our own solar system. Asteroids in the main belt are different from Kuiper belt objects, which are different from Oort cloud comets, which are different from the moons of the outer planets. Every region of the solar system has its own population of small bodies with distinct characteristics that reflect where and how they formed. If other star systems are similarly diverse, and there is no reason to think they are not, then the interstellar population should be diverse too. Some systems eject rocky planetesimals from their inner regions, some eject icy bodies from their outer regions, some eject both. Over billions of years, those ejected objects accumulate in interstellar space, filling the galaxy with a background population of rogue comets, asteroids, and possibly even rogue planets that are no longer bound to any star. That background population is invisible to us until one of its members happens to pass close enough to the Sun to be detected. The rate at which we detect interstellar objects depends on two things: how many of them there are, and how good our surveys are at finding faint, fast-moving targets. Early estimates, based on the discovery of Oumuamua, suggested there might be one detectable interstellar object passing through the inner solar system every year or so. The discovery of Borisov 2 years later seemed to support that estimate. The discovery of 3I Atlas 6 years after that suggests the rate might be even higher, but those numbers are biased by detection limits. The surveys that found these objects, Pan-STARRS, Atlas and others, are only sensitive enough to detect objects larger than a few hundred meters across. Smaller objects, the ones that are 10 or 50 meters across, pass through unnoticed. They are too faint. They move too fast. By the time anyone realizes they are there, they are already gone. The true rate of interstellar visitors could be 10 times higher, 100 times higher, we do not know. We only see the tip of the iceberg, the Vera the 100th. Rubin Observatory, which is expected to begin operations soon, will change that. Rubin has a mirror 8.4 meters across, and a camera with 3.2 billion pixels, the largest digital camera ever built for astronomy. It will survey the entire visible sky every few nights, imaging everything brighter than a certain threshold and looking for anything that moves or changes. Simulations predict that once Rubin is online, it will detect dozens of interstellar objects per year, maybe more. Instead of a handful of objects spread out over a decade, astronomers will have a steady stream of targets to study. That flood of data will answer some of the questions that 3 objects cannot. Are interstellar objects more like comets or more like asteroids? Do they cluster in certain size ranges, or are they evenly distributed? Are there compositional trends that point to common formation environments? Do they arrive from random directions, or do some directions produce more visitors than others? All of those questions require statistics, and statistics require large sample sizes. 3 objects is not a large sample. 50 objects is better. 500 objects is where you start to see real patterns. One of the patterns researchers are looking for is the ejection mechanism. How do objects end up in interstellar space in the first place? The leading theory points to gravitational interactions during planetary formation. When a planetary system is young, the orbits of the giant planets are not stable. They migrate inward or outward, driven by interactions with the disk of gas and dust they are embedded in. As they migrate, they scatter smaller bodies. Some of those bodies get kicked into the inner system and become asteroids. Some get kicked into the outer system and become comets. And some get kicked hard enough that they escape the star's gravity entirely and become interstellar wanderers. Simulations of this process suggest that for every planetary system that forms, a significant fraction of the initial solid material gets ejected. Some estimates put the fraction as high as 10 or 20%. If that is correct, then the galaxy is full of material that used to be part of planetary systems but is not anymore. Trillions upon trillions of objects ranging in size from dust grains to entire planets, drifting through the dark. Most of them will drift forever. Some of them will pass close enough to another star to be captured temporarily or permanently, and a tiny fraction will pass close enough to a star with intelligent life and functioning telescopes to be noticed. That raises an interesting possibility. If interstellar space is full of ejected material, and if that material includes not just rocks and ice but also organic molecules, the building blocks of life, then interstellar objects could be transporting complex chemistry across the galaxy. This idea, called panspermia, is not new. It was proposed more than a century ago by scientists like Svante Arrhenius, who suggested that life might spread between planets or even between star systems by hitching a ride on comets or meteorites. The idea fell out of favor for a while because it seemed too speculative and because there was no evidence for it. But the discovery of interstellar objects has brought it back into the conversation. The argument goes like this: life, or at least the chemistry that could lead to life, might not be unique to Earth. Organic molecules, amino acids, nucleobases, the kinds of compounds that biology is built from, have been found in meteorites, in comets, in interstellar clouds, and in the atmospheres of planets and moons throughout the solar system. If those compounds are common in space, then any icy body, comet or asteroid, that spends time in a region where liquid water is present could become a laboratory for prebiotic chemistry. If that body is later ejected and spends millions of years drifting through interstellar space, it carries whatever chemistry was happening on its surface or in its interior with it. If the body eventually gets captured by another star system or passes close enough to a planet with the right conditions, it could deliver that chemistry. Not life, necessarily. Bacteria or microbes are unlikely to survive the harsh radiation and cold of interstellar space for millions of years. But organic molecules, the chemical precursors to life, are much more robust. They can survive in frozen ice, shielded from radiation, for timescales far longer than a typical interstellar journey. If those molecules end up on a planet with liquid water, they could contribute to whatever chemistry is already happening there. They could, in principle, jumpstart the process of life in a system that otherwise would have taken longer to get there on its own. This is speculative. There is no direct evidence that interstellar objects have transported life or prebiotic chemistry between star systems. But the discovery that interstellar objects exist and pass through planetary systems regularly makes the idea plausible in a way it was not before. If objects like 3I Atlas are common, and if even a small fraction of them contain organic material, then the galaxy is not a collection of isolated systems. It is a network. Material, and potentially chemistry, flows between systems on timescales of millions of years. That flow could have consequences for how life arises and spreads. The other implication of interstellar objects is what they tell us about galactic dynamics. The galaxy is not static. Stars orbit the galactic center, but not in neat circular paths. They wobble, they interact with each other, they pass through regions of higher and lower density. Those interactions stir the interstellar medium, the gas and dust between the stars, and they also stir the population of small bodies drifting through that medium. When an interstellar object passes through a planetary system, its trajectory gets bent by the gravity of the star and planets. Most of the time, that bending is not enough to capture the object. It swings past and leaves. But occasionally, if the geometry is just right, and if the object passes close enough to a planet at just the right speed, it can be captured. Not permanently. The orbits of captured interstellar objects are typically unstable. They might stick around for a few thousand or a few million years before another gravitational interaction kicks them back out. But during that time, they become part of the system. They orbit the star, they interact with other bodies, and from the perspective of anyone living in that system, they look like natives. Some researchers have suggested that a fraction of the objects in our own solar system might be captured interstellar visitors, not the planets, not the large moons. But some of the asteroids, some of the comets, maybe some of the small irregular moons of the outer planets could have originated in other star systems and been captured by the Sun's gravity at some point in the past. There is no way to prove that without detailed chemical analysis, and even then the evidence would be circumstantial. But the possibility is there. The larger point is that the boundaries between star systems are not as sharp as we used to think. Material leaks out. Material leaks in. Over billions of years, the cumulative effect of that leakage is that every star system in the galaxy has been touched, in some small way, by material from other systems. The solar system is not an isolated island. It is part of a larger ecosystem, and interstellar objects are the threads that connect it to the rest of the galaxy. That changes the way we think about planetary formation. The standard model assumes that everything in a planetary system formed from the same protoplanetary disk, and that disk was chemically homogeneous, or nearly so. Variations in composition are explained by temperature gradients. The inner regions of the disk are hot, so only refractory materials, rock and metal, can condense there. The outer regions are cold, so ices can condense as well. That temperature gradient explains why the inner planets are rocky and the outer planets are icy and gas-rich. It is a clean story and it fits most of the data. But if material from other star systems is being mixed in, the picture gets messier. The protoplanetary disk is not just made of local material, it contains a small but non-zero fraction of interstellar debris that was captured as the Sun moved through the galaxy. That debris carries a different chemical signature, different isotope ratios, different organic molecules, different minerals. When that debris gets incorporated into forming planets and comets, it adds noise to the signal. It makes the chemistry of the solar system slightly less uniform than it would have been otherwise. How much noise? We do not know. The fraction of interstellar material in the early solar system was probably small, maybe a fraction of a percent, but small does not mean negligible. If you are trying to understand the fine details of planetary chemistry, the isotope ratios of water on Earth, the distribution of organic molecules in meteorites, the composition of cometary ice, you have to account for the possibility that some of that material came from somewhere else. Interstellar contamination, if you want to call it that, is part of the background. The same logic applies to other star systems. If we ever detect biosignatures on an exoplanet, chemical signatures in the atmosphere that suggest the presence of life, we will have to ask whether those signatures reflect life that originated on that planet or life that was delivered by an interstellar object. That distinction matters. If life arises independently on multiple planets, that tells us life is common and the conditions for its emergence are not especially rare. If life arises once and spreads via interstellar panspermia, that tells us life is rare but persistent. Both scenarios are possible. Both would be scientifically profound, but they lead to very different conclusions about the prevalence of life in the universe. Interstellar objects are also a logistical challenge. Right now, we study them passively. We detect them, we track them, we point telescopes at them and collect whatever light we can. What we cannot do is visit them, not with current technology. Every interstellar object detected so far has been discovered after it was already on its way out of the solar system. By the time anyone realized what they were looking at and started planning a mission, the object was months or years away and moving at speeds that no spacecraft could match. The European Space Agency has a mission called Comet Interceptor that is designed to address this problem. The spacecraft is scheduled to launch in 2029 and will be parked at a gravitationally stable point called Sun-Earth Lagrange Point 2, about 1.5 million kilometers from Earth. It will wait there, in hibernation mode, until a suitable target appears. A long-period comet falling into the inner solar system for the first time, or an interstellar object passing through. When the target shows up, Comet Interceptor will wake up, detach from its parking spot, and intercept the object while it is still close enough to reach. The spacecraft is designed to split into 3 modules that will fly past the target from different angles, imaging it, measuring its composition, and collecting dust samples from the coma. Comet Interceptor is a gamble. It assumes a suitable target will appear within a reasonable time frame after launch. If no comet or interstellar object shows up, the mission will sit in orbit doing nothing. But if a target does appear, and if the geometry works out, Comet Interceptor will be the first spacecraft ever to study an interstellar visitor up close. That data would be orders of magnitude better than anything we can get from ground-based telescopes. High-resolution images showing surface features, direct measurements of the gas and dust composition, maybe even samples of material ejected from the nucleus that could be analyzed in detail. The challenge with interstellar objects is that they move on hyperbolic trajectories, which means they are not coming back. If you miss the intercept window, you have lost your chance. There is no second opportunity years later when the object swings around again. The mission has to be fast and flexible. You need a spacecraft that is already in space, already fueled, already pointed in roughly the right direction. And you need tracking systems that can detect the object early enough to give the mission planners time to calculate an intercept trajectory and execute the burn. Comet Interceptor is designed to meet those requirements, but it is still limited by how far the spacecraft can travel and how much fuel it has. If the target is too far away or moving too fast, the mission might not be able to reach it. NASA has studied the feasibility of similar missions. The conclusion is that interstellar intercepts are technically possible, but require advanced propulsion systems, solar sails, ion drives, maybe even nuclear thermal propulsion. Chemical rockets, the kind we use for most space missions today, do not have the delta V, the change in velocity needed to catch up to an object moving at 60 or 70 kilometers per second. You would need something faster, something that can accelerate continuously over weeks or months, instead of burning for a few minutes and then coasting. Those technologies exist in theory. Some of them exist in prototype form, but they have not been deployed on operational missions yet. The other option is to get lucky. If an interstellar object happens to pass very close to Earth, close enough that a fast mission could reach it with current propulsion, and if we detect it early enough, a rapid response mission could be launched. The spacecraft would not have to be fancy. A simple flyby probe with a camera and a spectrometer could collect data that would dwarf anything we can get from telescopes, but the timing has to be perfect. The object has to be close, it has to be discovered early, and the mission has to be approved, funded, built, and launched in a matter of months. That has never happened. It probably will not happen anytime soon, but the possibility is there. In the meantime, the best strategy is to find more interstellar objects and study them from afar. Each new detection adds to the dataset. Each set of observations refines the models, and each object teaches us something about the conditions in other star systems and the processes that fill interstellar space with debris. The Vera, the 100th Rubin Observatory, will be the primary tool for that work over the next decade. Once it is operational, it will survey the sky relentlessly, catching faint, fast movers that current surveys miss. The data will go into a central archive where researchers can search for patterns. How many interstellar objects are there? What are their size distributions? What are their compositions? Where are they coming from? Those questions are not just about cataloging objects. They are about understanding how planetary systems evolve and how the galaxy recycles its material. Every star that forms does so from a cloud of gas and dust that contains atoms forged in previous generations of stars. Those atoms were scattered into space by supernovae and stellar winds, mixed into the interstellar medium, and then collapsed into new stars and planets. The same process happens with solid material. Rocks and ice from old planetary systems get ejected, drift through space, and sometimes get incorporated into new systems. The galaxy is a giant recycling program, and interstellar objects are the shipping containers. What we are learning piece by piece, object by object, is that the universe is more connected than we thought. The stars are not isolated. The planetary systems are not separate. Everything is part of a larger flow of matter and energy that spans the galaxy and operates on timescales of billions of years. Interstellar objects are the visible evidence of that flow. They are messengers, carrying information about places we cannot visit and times we cannot witness. And for a brief moment, as they pass through our neighborhood, we get to read the messages. 3I Atlas is one of those messengers. It came from somewhere else. It is heading somewhere else. And in the few months we had to study it, we learnt a little bit about what it is and where it might have come from. Not enough to answer all the questions, not nearly enough, but enough to know that it is worth looking for the next one, and the one after that. Because every interstellar object that passes through the solar system is a chance to see the galaxy from a new angle, to sample material from another star system, to test theories about how planets form and how matter moves between the stars, and to be reminded once again that we are not isolated. We are part of something much larger, something that stretches across light years and billions of years, connecting every star and every planet in a network that we are only beginning to understand. The fading light of 3I Atlas, as it moves outward into the dark, is carrying that message with it. And somewhere, in another system, around another star, something else is starting its own journey. Something that, millions of years from now, might pass close enough to the sun to be noticed. And when it does, the telescopes will turn, the alerts will go out, and the process will start all over again. By the time December arrives and 3I Atlas reappears from behind the sun, the object will be leaving. Not in the metaphorical sense, not in the slow drift of an asteroid crossing the sky over months or years, leaving in the permanent, irreversible sense. Every second, the distance between this comet and the solar system increases by 61 kilometers. Every hour, it moves 220,000 kilometers farther away. Every day, more than 5 million kilometers. By the end of December, it will be farther from the Sun than Jupiter. By the end of the year, farther than Saturn. Within a decade, it will cross the orbit of Neptune and enter the outer reaches of the solar system where sunlight is barely a whisper and the only company is the distant frozen bodies of the Kuiper Belt. And then it keeps going, past the Kuiper Belt, past the scattered disk, past the heliopause, the boundary where the sun's influence gives way to the pressure of interstellar space. Within a few hundred years, 3I Atlas will be farther from the sun than any human-made object, farther than Voyager 1, which has been traveling since 1977 and is currently the most distant artifact of human civilization. Farther than the Pioneer probes, the New Horizons spacecraft, any satellite or piece of debris we have ever launched. The comet will keep moving, silent and dark, through a void so empty that the nearest star might be light years away, and the only light will be the faint glow of distant galaxies scattered across the sky like dust. It will move through that emptiness for millions of years, tens of millions possibly, the same way it has already been moving for millions of years before it arrived here. Eventually, billions of years from now, it might pass close enough to another star to be noticed by whatever instruments or intelligences are watching that star's neighborhood. Or it might not. The galaxy is large, stars are far apart. The odds of any given interstellar object passing through another planetary system are low. Most of them drift forever, unseen, unnoticed, carrying their cargo of frozen history through an eternity of darkness. That is the reality of interstellar objects. They are fleeting, not because they move quickly, though they do, but because the window of opportunity to study them is absurdly narrow. 3I Atlas was detected in July 2025. By September, it had disappeared into the sun's glare. When it re-emerges in December, it will be faint, receding and dimming steadily. Within months, it will be too faint for all but the largest telescopes to see. By mid-2026, it will be gone from every observing schedule, reduced to a footnote in the archive of orbital data, a dot on a trajectory plot that extends outward into empty space and never comes back. In that narrow window, from July to September, and again from December to maybe March or April, astronomers around the world collected every scrap of data they could: photometry tracking the brightness variations, spectra measuring the composition of the coma, astrometry pinning down the position and refining the orbit. Every observation added a small piece to the puzzle. And when the object fades beyond detectability, the puzzle will still be incomplete. That is not failure, that is the nature of the work. You gather what you can, you analyze what you have, and you accept that some questions will remain unanswered. So what did we learn? What did this brief encounter actually tell us? Start with the trajectory. The orbit is hyperbolic, that much is certain. The eccentricity is greater than 1, meaning the object is not bound to the sun and will not return. The incoming velocity was high, about 61 kilometers per second relative to the sun, which places it well above solar escape velocity. The trajectory, when traced backward and corrected for the motion of the sun through the galaxy, points roughly toward the constellation Sagittarius, in the direction of the galactic center. That does not tell us which star the object came from, but it does tell us the general region of the galaxy it passed through on its way here. Somewhere along that line of sight, hundreds or thousands of light-years away, there is a planetary system that used to have one more comet than it has now. The composition is where things get messier. Spectroscopy confirmed water vapor in the coma. That was expected. Water is common in comets, both in our solar system and, apparently, in others. But the other volatiles, the carbon monoxide, carbon dioxide, methane, ammonia that normally show up in cometary spectra, were either missing or present at levels far below what standard models predict. That could mean the object is depleted in those compounds. Or it could mean they are trapped beneath a thick insulating layer of dust that prevents them from sublimating efficiently. Or it could mean the object formed in a region of its home star system where those ices did not condense, which would tell us something about the temperature profile of that system's protoplanetary disk. We do not know which explanation is correct. The data is not detailed enough to distinguish between them. What we do know is that 3I Atlas does not fit the profile of a typical Oort cloud comet from our own solar system. It is less active, it outgasses less material, its coma is fainter, its tail, if it has one, is too faint to see clearly. That makes it different. Whether that difference reflects something about the object's origin, its composition, or its thermal history is still an open question. The size is uncertain. Estimates based on brightness and assumed surface reflectivity put the nucleus somewhere between 440 meters and 5.5 kilometers across. That is a huge range, more than an order of magnitude. The uncertainty exists because we do not know how reflective the surface is. If the surface is dark, like the carbonaceous asteroids that make up much of the main belt, the object has to be large to produce the observed brightness. If the surface is brighter, the object can be smaller. Hubble observations in late August confirmed the presence of a coma, but could not resolve the nucleus itself. The object is too small and too far away for even Hubble to image it as anything more than a point of light. The shape is even more uncertain. Light curve data, the measurements of how the object's brightness changes over time, suggest it might be highly elongated. Some models fit the data with an axis ratio of 5:1 or higher, meaning the long dimension is 5 times longer than the short dimension. That would make it similar to Oumuamua, the first interstellar visitor, which was estimated to have an axis ratio of at least 6:1. But light curves can be misleading. If the object is irregularly shaped, or if its surface has bright and dark patches that rotate into and out of view, the brightness variations can mimic the signal of an elongated object, even if the shape is more mundane. Without resolved images or radar data, which we do not have and will not get, the shape remains ambiguous. The activity level is low. That much is clear. Hubble detected a coma, which means the object is outgassing and behaving like a comet. But the rate of outgassing is far below what you would expect for a pristine icy body making its first pass through the inner solar system. Most comets from the Oort cloud, the distant reservoir of icy bodies that surrounds our solar system, become extremely active when they fall inward toward the sun. The ice on their surface has never been heated. When it hits sunlight for the first time in billions of years, it sublimates vigorously, producing bright comas and long tails. 3I Atlas is not doing that. Its activity is weak, more like a comet that has already made multiple passes near the sun and developed a thick crust of non-volatile material on its surface. But 3I Atlas has not made multiple passes. This is its first time through any star system in millions of years. So either the object formed with a mantle already in place, or its ice composition is different enough that it does not sublimate the way we expect, or something about its structure, porosity, internal voids, is inhibiting the outgassing. That is what we learned. A hyperbolic trajectory, water vapor in the coma, weak activity, uncertain size and shape, possible depletion of volatiles other than water, and an origin somewhere in the direction of Sagittarius, but otherwise unidentified. Not a long list, not a complete picture, but more than we knew before the object arrived, and more than we will know again until the next interstellar visitor shows up. What we did not learn is just as important. We did not learn where the object came from, not which star, not which planetary system. We have a direction, but directions are not addresses. The object could have been ejected from a system 500 light-years away or 5,000. It could have been traveling for a few million years or a few 100 million. The longer it has been traveling, the more the stars have moved, and the harder it becomes to trace the trajectory backward to a specific source. Gaia, the European Space Agency's mission that has mapped the positions and motions of more than 1 billion stars in the Milky Way, gives us a detailed snapshot of where the stars are now and how fast they are moving. But reversing those motions over millions of years accumulates errors. Small uncertainties in stellar velocities become large uncertainties in past positions. After a few million years, the backwards projection becomes too noisy to identify a single star as the source. The object came from somewhere in that general region of the galaxy. That is as precise as we can get. We did not learn the detailed chemistry. Spectroscopy gave us water vapor and hints of dust, but the lines for other volatiles, the ones that would tell us about the carbon-to-oxygen ratio, The nitrogen abundance, the isotope ratios of hydrogen and oxygen were too weak or too noisy to measure confidently. Those details matter because they encode information about the conditions in the protoplanetary disk where the object formed. The temperature, the pressure, the elemental abundances, all of it leaves a fingerprint in the chemistry. Without those measurements, we cannot compare the object's composition to models of planetary formation in different types of star systems. We cannot say whether it formed around a star similar to the Sun or a star that was hotter, cooler, older, younger, more metal-rich, more metal-poor. The data is not there. We did not learn whether the object is typical or unusual. 3 interstellar objects is not a large sample. Oumuamua was dark, elongated, showed no visible outgassing, and accelerated in a way that did not fit comet models. Borisov was bright, active, had a visible coma and tail, and looked like a normal comet. 3I Atlas is somewhere in between. It has a coma, but the activity is weak. It might be elongated, but the evidence is not conclusive. Its composition is stripped down, but we do not know if that is because it is genuinely unusual or because we are not measuring it correctly. With 3 data points, you cannot say which one is the outlier and which one is the norm. You need dozens of objects, hundreds, before patterns start to emerge. Until then, every interstellar visitor is a surprise, and every surprise raises more questions than it answers. We did not learn what caused the weak activity. The leading hypotheses point to either a thick insulating mantle of dust on the surface or an unusual ice composition that sublimates less efficiently than the water and carbon monoxide we are used to seeing in solar system comets. Both explanations are plausible. Neither can be confirmed or ruled out with the data we have. The answer might come from future observations of other interstellar comets. If most of them show similarly weak activity, that tells us something systematic is going on. Maybe interstellar comets in general develop mantles because they spend so much time in the cold of interstellar space that their surfaces get heavily processed by cosmic rays. Maybe the ice in other star systems is compositionally different enough that sublimation rates do not match our models. If most interstellar comets turn out to be highly active like Borisov, then 3I Atlas is the outlier and we need to explain what makes it different. Right now we do not know. What we also did not learn, and this is probably the most frustrating gap, is whether the object is natural or artificial. That sentence is going to sound absurd to most readers. Of course it is natural. It is a comet. It has a coma. It is outgassing water vapor. What else could it be? The question is not serious in the sense that most scientists think 3I Atlas is anything other than a rock and ice ball from another star system. But the question persists because Oumuamua left it open. Oumuamua accelerated without visible outgassing, and no one could definitively explain why. That ambiguity gave rise to speculation about artificial objects, light sails, probes, debris from another civilization. The speculation was not mainstream. Most researchers rejected it on the grounds that natural explanations, however incomplete, were more plausible than invoking alien technology. But the speculation was not completely dismissed either, because the data left room for it. 3I Atlas does not have that ambiguity. It is outgassing. It has a coma. The behavior fits the comet model well enough that no one is seriously proposing exotic alternatives. But the broader question, whether any interstellar object we detect could be artificial, remains philosophically open. If other civilizations exist in the galaxy, and if they have developed technology capable of interstellar exploration, then artifacts from those civilizations might be out there. Derelict spacecraft, discarded propulsion stages, intentional probes designed to visit other star systems and report back. The galaxy is old. If even a small number of civilizations have reached that level of technology over billions of years, the cumulative output of artifacts could be significant. Not large enough that we trip over them constantly, but large enough that one might, by pure chance, pass through a planetary system where someone is watching. The argument for taking this seriously is not that we have evidence. We do not. The argument is that the cost of looking is low. Every time we detect an interstellar object, we are already pointing telescopes at it. We are already measuring its trajectory, its brightness, its spectrum, adding a check for anomalous properties, unusual acceleration, non-random surface features. Anything that does not fit natural models costs almost nothing. Most of the time the check will come back negative. The object is natural, but if the check ever comes back positive, if we ever find an interstellar object that cannot be explained by standard astrophysics, the implications would be profound, not just scientifically, civilizationally. The discovery of an artifact from another civilization would rewrite our understanding of our place in the universe overnight. That is not what happened with 3I Atlas. The object is consistent with being a natural comet. But the fact that the question is even being asked tells you something about how the discovery of interstellar objects has shifted the conversation. Before Oumuamua, the idea of finding an interstellar visitor was theoretical. We knew they had to exist, but we had never seen one. Now, in less than a decade, we have seen 3. That changes the mental landscape. Interstellar objects are real. They pass through the solar system regularly, and each one is a black box. We do not know what is inside until we open it, and opening it requires time, resources, and luck. Most of them will be rocks or ice balls, mundane in the sense that they obey the same physical laws as everything else in the universe. But the possibility that one of them could be something else, something we did not predict, is no longer abstract. The scientific debate around 3I Atlas is far from settled. Researchers are still analyzing the data. Light curves are being refit with new models. Spectra are being reprocessed with better calibration. Orbital parameters are being refined as more observations trickle in from observatories that caught the object during its brief visibility window. Some of those analyses will be published in peer-reviewed journals over the next year or two. Others will sit in archives waiting for someone to come along with a new idea or a new technique that can extract more information from the same data. The outstanding questions will drive that work. What is the object's true size and shape? What is its surface composition? Why is the activity level so low? Does it contain carbon monoxide and carbon dioxide, or are those compounds genuinely absent? Is the orbit being affected by non-gravitational forces? And if so, how large is the effect? Can we trace the trajectory backward with enough precision to identify a plausible source star, or is the origin permanently lost in the noise of stellar motions? All of those questions are answerable in principle. Whether they get answered in practice depends on whether the data is good enough and whether someone cares enough to do the analysis. Some questions will remain unanswered no matter how much effort goes into the analysis. The detailed internal structure of the object, whether it is a solid chunk or a rubble pile, whether it has voids or layers or a differentiated interior, cannot be determined from brightness measurements and spectra. You need seismic data, or radar, or a spacecraft that flies close enough to measure the object's gravitational field. None of those are happening. The object is already too far away and moving too fast. By the time anyone could design and launch a mission, it would be decades out of reach. The internal structure will remain a mystery. The same is true for the surface features. Does the nucleus have craters, smooth plains, active vents, bright and dark patches? We have no idea. Hubble could not resolve the surface. Ground-based telescopes could not resolve the surface. The object is too small and too faint. All we have is the integrated light from the entire nucleus, plus whatever contribution comes from the coma. That integrated light tells you the average properties, but it does not tell you the details. To see the surface, you need to get close. Meters, not millions of kilometers. That is not happening either. What 3i Atlas has done, despite all the gaps and uncertainties, is refine our understanding of what interstellar objects are and how they behave. Each new detection adds to the dataset. Each dataset makes the models a little more robust. Before Oumuamua, we had 0 confirmed interstellar objects. Theoretical models predicted they should exist, but those predictions were untested. Oumuamua confirmed the models were right. Interstellar objects are out there. They do pass through planetary systems, and we can detect them if we are looking. Borisov confirmed that some of them look like normal comets, at least from a distance. 3i Atlas is adding nuance. It is saying that interstellar objects are diverse. Some are active, some are inert, some are in between. Some are bright, some are dark, some are faint. Some match the properties of solar system comets, some do not. That diversity is exactly what you would expect if the interstellar population reflects the diversity of planetary systems across the galaxy. The lasting impact on planetary defense protocols is harder to quantify but no less real. 3i Atlas was not a threat. It was never going to hit Earth. But the detection and tracking process, the alerts that went out within hours of discovery, the rapid orbital calculations that confirmed the trajectory was hyperbolic and the closest approach was far beyond any danger threshold, all of that worked exactly as designed. The system was tested. The system passed. That is valuable. Because the next object that shows up moving that fast might not be an interstellar visitor on a safe flyby. It could be a long-period comet from the Oort cloud on a trajectory that brings it uncomfortably close to Earth. And when that happens, the response will depend on the same detection networks, the same tracking algorithms, the same coordination between observatories and space agencies that processed 3i Atlas and delivered a clear answer in a matter of days. The broader lesson for planetary defense is that speed matters. Comets from the Oort cloud and interstellar objects are different from main belt asteroids in one critical way. They show up late. Asteroids in stable orbits can be catalogued years or decades in advance. Their positions are predictable. Their trajectories are well understood. You know where they are going to be months or years into the future, and if one of them is on a collision course, you have time to plan a deflection mission. Comets and interstellar objects do not give you that luxury. They appear suddenly, move fast, and by the time you have figured out what they are and where they are going, they might already be past perihelion and heading back out. If one of them is on a collision course, the warning time could be weeks or months, not years. That compresses the decision-making process. It puts enormous pressure on the detection and tracking systems to deliver accurate data quickly. 3i Atlas was a dry run. The object was not dangerous, but the timeline was real. The speed was real. The uncertainties in the early orbital calculations were real. And the global observing campaign that followed the discovery, the dozens of telescopes that dropped their scheduled programs and pointed at this one target, demonstrated that the infrastructure is there and it works. For observational astronomy, the encounter reinforced a lesson that has been building over the last decade. Transient events matter. The sky is not static. Things appear, things change, things disappear. If you are only observing the same targets over and over, you miss the transience. If you are not surveying the sky repeatedly, you miss the fast movers. Interstellar objects are the ultimate transients. They show up once, they move through, they leave. You get one chance to study them. If you miss the window, you do not get a second chance years later when the object comes back around. That reality is driving the next generation of survey telescopes. Rubin is being built specifically to catch transients, wide field, fast cadence, sensitive detectors. The goal is to image the entire visible sky every few nights and catch everything that moves or changes. Once Rubin is operational, the number of detected interstellar objects will go from a handful per decade to dozens per year, maybe more. That flood of data will transform the field. Instead of analyzing 3 objects and trying to infer general trends, astronomers will have hundreds of objects with well-measured properties, size distributions, composition distributions, trajectory distributions. All of it will come into focus. The questions that are unanswerable with 3 objects will become answerable with 300. But even with hundreds of objects, some mysteries will persist. The origins will still be hard to pin down. You will know the directions the objects came from, but tracing those directions back to specific stars will still be noisy and uncertain. The detailed chemistry will still require close-up measurements that are beyond the reach of ground-based telescopes. The internal structures will still be hidden. The only way to really understand what interstellar objects are, in the detailed physical sense, is to visit one. Send a spacecraft, image it, sample it, bring material back to Earth, and analyze it in a lab. That is not impossible. It is just hard and expensive, and it requires planning and infrastructure that do not exist yet. Comet Interceptor, the European Space Agency mission scheduled to launch in 2029, is a step in that direction. The spacecraft will park at a gravitationally stable point in space and wait for a target to appear. When a suitable comet or interstellar object shows up, the mission will wake up and intercept it. That is the plan. Whether it works depends on whether a target appears within a reasonable time frame and whether the geometry allows an intercept. If it does, Comet Interceptor will be the first mission to study an interstellar visitor up close. The data will be transformative. Images showing surface features at meter-scale resolution, spectra of gas and dust collected directly from the coma, maybe even samples of material ejected from the nucleus that can be analyzed in situ. That data will answer questions that telescopes cannot. It will also raise new questions, the way close-up data always does. But it will move the field forward in ways that remote observations alone cannot. In the meantime, the fading light of 3I Atlas is all we have. By the time you read this, the object is already farther from the Sun than it was when it was discovered. It is dimming. The coma is shrinking as the rate of sublimation drops with distance. The dust is dispersing. Within months, the object will be too faint for any telescope on Earth to see. The data collection will stop. The observations will end. And the object will continue its journey outward into the dark, carrying its cargo of frozen history into the void. That journey is a reminder of scale, not just the scale of space, though that is part of it, the scale of time. 3I Atlas has been traveling for millions of years. It will keep traveling for millions more. Human civilization, all of recorded history, the entire span from the first cities to the present day, fits into a sliver of that timeline. The comet was already in motion long before humans existed. It will still be in motion long after we are gone. What we saw during those few months in 2025 was a momentary intersection. 2 trajectories, ours and the comet's, crossed paths briefly. We looked. We measured. We learned what we could. And then the paths diverged and the comet moved on. But something remains, not the object itself. That is gone. What remains is the data, the measurements, the spectra, the orbital parameters, the images. All of it archived, stored, available to anyone who wants to look at it. Future researchers, working with better models or better techniques, will revisit that data. They will find patterns we missed. They will answer questions we could not. The encounter is over, but the science is not. The science continues as long as someone is willing to ask questions and look for answers in the data we collected. And the next object is already on its way. Somewhere out there, drifting through interstellar space, another comet or asteroid or fragment is moving toward the solar system. It might arrive next year, it might arrive in a decade, it might not arrive for a century, but it is coming, and when it does, the telescopes will turn, the alerts will go out, the tracking will begin, and the process will start all over again. Each new visitor bringing its own mysteries, its own surprises, its own brief window into the universe beyond our star. That is what 3i Atlas leaves behind. Not answers, questions, better questions than we had before, and the knowledge, hard-won and fleeting, that the galaxy is full of things we have only just begun to understand, objects moving through the dark, carrying stories from places we will never visit, passing through our neighborhood just long enough for us to glimpse what they are and wonder where they came from. The echo is fading, the object is leaving, but the questions it raised are staying, and those questions will shape the next decade of interstellar object research, planetary defense planning, and our slowly expanding understanding of what exists in the space between the stars. The window was brief, the view was partial, but for a moment we saw something from beyond. And that is more than we had before the summer of 2025, when a machine in Chile noticed something wrong and the chase began. So here is what we are left with. A machine in Chile noticed something that should not have been there. A dot of light moving too fast, aimed in the wrong direction, carrying a trajectory that pointed backward into the space between stars. We pointed telescopes at it. We measured its brightness, calculated its speed, searched its spectrum for clues. We learned that it was icy, faint, oddly quiet for something making its first pass near a sun in millions of years. We learned that it came from somewhere in the direction of Sagittarius, though which star and which system remain mysteries we will likely never solve. We learned that it was leaving, that it would not return, that the window to study it was closing faster than anyone wanted, and then it faded. Not because it stopped existing, but because it moved beyond the reach of our instruments, back into the darkness it came from. By now, it is farther from the Sun than Jupiter, in a few years, farther than Neptune, in a few centuries, farther than anything humanity has ever built. It will keep moving, silent and frozen, through a void so empty that the light of the nearest star is years away. It has been doing this for longer than our species has existed. It will keep doing it long after we are gone. What lingers is not the object itself. What lingers is the realization that the galaxy is not a collection of isolated islands. It is a network. Material flows between stars on timescales we can barely comprehend. Every rock, every comet, every frozen shard drifting through the dark